The measure of any journey begins with the clocks that already exist on Earth, because human time is first built from repeating cycles that can be trusted. Earth turns once on its axis, and this rotation sets the day. Earth also travels once around the Sun, and this orbit sets the year. These two cycles are not only cultural markers, but physical processes that remain steady enough to support navigation and measurement. A long journey in space is therefore easiest to describe using days, months, and years, because those units are anchored in the motion of the homeworld. When a destination is far, the question becomes how many Earth days must pass before arrival, how many Earth months mark the passage of distance, and how many Earth years fit inside the full travel time. This is the foundation of human time, not as a private feeling, but as a shared calendar that stays the same whether a person is at sea in a city or in a spacecraft. The first step towards Saturn is therefore not Saturn itself. It is a stable way to count time that does not change when the sky changes. Earth supplies that stability through rotation orbit, and the ability to build clocks that divide those cycles into smaller parts. Modern timekeeping uses vibrations in atoms to define the second with extreme precision, but the everyday meanings of day and year remain tied to Earth's motion. Even when atomic clocks keep time more steadily than Earth's rotation, the day is still the unit used to describe sleep work and the passage of weeks, and the year is still the unit used to describe seasons and long plans. When the journey is described in human time, it is described in these familiar units, and the entire problem becomes a conversion between distance and time through speed. Speed in the simplest sense is distance divided by time. Yet the moment the destination is a planet, the distance is not a fixed number because planets move. Earth moves along its orbit. Saturn moves along its orbit. The line between them changes length every day. This means the journey time cannot be stated as a single number without also describing the route and the departure and arrival conditions. Still, human time needs an anchor, and the anchor begins with the scale of ordinary movement on Earth. A person walking on level ground covers a few kilometers in an hour at a steady pace. A bicycle can cover more. A car on a highway covers tens of kilometers in an hour. A fast train can cover hundreds of kilometers in an hour. A long-haul airplane crosses continents and oceans in hours, not days, moving at close to 1,000 kilometers per hour. These benchmarks are not used because they can be extended directly to space. They are used because they show what fast means in daily life, and because they make clear how quickly intuition breaks when speeds increase. The jump from walking to flight is already a jump of hundreds of times in speed, and yet even flight remains slow compared with orbital motion. Earth's surface moves due to rotation, and a point near the equator travels thousands of kilometers in a day. Earth's orbital motion around the Sun is faster still, carrying the planet through space at tens of kilometers each second. That speed is not felt because everything on Earth shares it, but it matters because a spacecraft leaving Earth begins by already sharing Earth's orbital motion, and any journey to another planet is built on changes to that motion. Human timekeeping remains steady, but the environment of motion expands. The journey to Saturn is therefore not a straight dash outward like a car on a road. It is a sequence of speed changes and curved paths determined by gravity, with the Sun as the dominant central mass. Before any route is chosen, how long must be tied to the kind of motion that can be achieved. In human time, a day is long enough for a ship to cross a significant stretch of ocean. A month is long enough for seasons to begin to shift. A year is long enough for a full cycle of weather and sunlight. Space travel changes the scale. A spacecraft can reach the moon in a few days. That already shows that days can measure travel beyond Earth. Yet Saturn is vastly farther away than the moon, and reaching it requires leaving the near-Earth region and moving outward into the solar system. In this first section, the goal is not to calculate Saturn's distance. It is to build the time language that will later hold that distance without strain. Human time can stretch to years without losing meaning because people use years to describe education growth and the span of projects. Space missions are also planned in years. A spacecraft can be designed, built, launched, cruise for years, and arrive with its instruments still working. So the question of reaching Saturn is naturally expressed in years, not in days. Days and months remain useful for the early phase of a mission and for describing schedules, but years become the natural container for the total flight. The meaning of how long also depends on what is being counted. There is travel time from launch to arrival, which is the cruise duration. There is also preparation time on Earth, which can be many years of engineering and testing, but that is not travel. There is communication time, the delay for radio signals to cross the distance at light speed, which becomes minutes and then more than an hour at Saturn distances. Communication delay is not travel time, but it changes how the journey is experienced and controlled, because actions and confirmations cannot be immediate. There is also time spent in the correct alignment waiting for a launch window when Earth and Saturn's positions allow an efficient route. Waiting for alignment is time that passes on Earth before the journey begins, and it can be expressed in months or years depending on mission constraints. When the phrase measured in human time is used carefully, it separates these categories. It refers mainly to cruise duration and to communication delay because those are the times that are imposed by distance and physics rather than by planning choices. Human time also includes human lifetime scales. A journey that takes a few years fits within the span of a single job and within the adult lifetime of the people who plan and operate it. A journey that takes decades still fits within a career, but begins to stretch across generations of teams and technologies. A journey that takes centuries does not fit comfortably into the social structures that support missions. This is why the conversion of Saturn travel into years is not only a mathematical step, it is a practical framing. It asks whether the journey can be completed within a timescale that people and institutions can sustain. In the age of robotic exploration, the answer has already been demonstrated in part by spacecraft that reach Saturn in years, not decades. But this section does not yet use those examples. It prepares the sense of time so that when mission durations appear, they can be understood as lived schedules rather than abstract numbers. The human experience of time in space also differs from the human experience on Earth, even when the same clocks are used. A spacecraft in cruise is in an environment without day and night in the usual sense. It may rotate for stability, but its clocks do not depend on sunrise. Still, mission control on Earth schedules actions according to Earth days and Earth hours. The spacecraft's operations are planned in timelines that mirror work cycles and sleeping cycles, even if the spacecraft does not sleep. The long cruise is divided into phases with quiet periods where the spacecraft coasts and periodic checkouts, where instruments and systems are tested. This division turns years into manageable blocks of months and weeks. It is another way human time remains relevant even in deep space. Yet the physical time that matters most to travel is the time it takes to change position in the solar system, and that depends on speed relative to the Sun. Here it is useful to establish one more benchmark: escape from Earth and entry into heliocentric travel. A rocket must first reach orbit, which is a speed of several kilometers per second relative to Earth. It then must leave Earth's gravitational hold enough to set a new path around the Sun. The time to reach orbit is minutes. The time to leave Earth's immediate region is hours to days. These times are small compared with the cruise to Saturn, but they show how a space journey contains both very short phases and very long phases. Human time accommodates both using minutes and hours for launch events and years for interplanetary cruise. A related benchmark is the speed of light because it sets the fastest possible communication. Light travels so fast that it crosses Earth. In a fraction of a second, crosses the Earth-Moon gap in a little more than a second, and crosses the Earth-Sun distance in minutes. When the destination is Saturn, Light time becomes long enough to matter in daily operations. Commands sent from Earth do not arrive instantly. Telemetry from the spacecraft does not return instantly. The mission is operated with this delay in mind, and the delay is counted in minutes when the spacecraft is near Earth, and in more than an hour when the spacecraft is near Saturn. Even without numbers yet, the shape of the problem is clear. Reaching Saturn is measured in years of travel and in tens of minutes to more than an hour of communication delay, with the exact values depending on where Earth and Saturn are in their orbits at the time. This section therefore establishes a calm framework. Human time is built from Earth's rotation and orbit. Human intuition for speed is built from walking, driving and flying, but space travel quickly exceeds those scales in velocity and distance. The journey to Saturn will be expressed not as a heroic race, but as a conversion problem, a moving distance, a chosen path shaped by gravity, and a speed profile limited by propulsion and energy. The next step will place Saturn in the solar system map, so that the distance to it can be described in a consistent way, and then human time can be attached to that distance through known routes and known spacecraft performance. Saturn's place is defined first by the shape and rhythm of the solar system, because travel time cannot be understood until the destination is located in the same moving frame as the departure point. The solar system is organized around the Sun, which holds most of the mass and governs the main gravitational field. The planets follow paths around the Sun that are close to a single plane, and those paths are close to circles but are slightly stretched into ellipses. Earth travels on an inner orbit. Saturn travels on an outer orbit. Both move in the same general direction around the Sun, and both keep a steady pace that can be described with a period the time required to complete one full circuit. Earth's period is 1 year by definition in human calendars. Saturn's period is much longer. It takes close to 30 Earth years for Saturn to complete one orbit around the Sun. This long period already hints at distance because in a gravity-governed system, outer planets move more slowly and have larger orbits. Yet Saturn's distance is not fixed in a simple way for travel, because Earth and Saturn are never standing still relative to each other. The simplest picture is to imagine two runners on concentric tracks, one on an inner track moving faster, and one on an outer track moving slower. The distance between them changes as their angular separation changes, even though each stays on its own track. In the solar system, the changing distance between Earth and Saturn is the first practical fact of the journey. The second practical fact is that almost all interplanetary travel is guided by the Sun's gravity. A spacecraft that leaves Earth is still orbiting the Sun even if it is leaving Earth's immediate vicinity. The path to Saturn is a heliocentric path. This means Saturn's location is best described not by a straight line distance from Earth on a given day, but by Saturn's orbit and Earth's orbit, and by how those orbits line up at departure and arrival. Saturn's average orbital distance from the Sun is about 9.5 times the Earth-Sun distance, though. The value varies slightly because of orbital eccentricity. Earth's orbital distance varies slightly as well, but by a smaller fraction. These relative distances matter because they set the energy required to move from Earth's orbit to Saturn's orbit. A spacecraft must increase its distance from the Sun, which requires raising the orbit's size. In orbital mechanics, raising an orbit generally means increasing the spacecraft's heliocentric speed at the right place near the Sun so that the new path reaches farther out. The destination is not an object in a fixed direction. It is a moving planet on a distant orbit, and the route must meet it at the right time and place. Saturn's orbit is not only large, it is also slow in angular motion compared with Earth. Earth completes a circle in 1 year. Saturn advances only a small fraction of its orbit in the same time. This difference sets the rhythm of opportunities. When Earth and Saturn are aligned with the Sun in a way that supports a relatively efficient transfer, a launch window exists. The window is not a single moment. It is a span of days or weeks when departure conditions allow a planned trajectory to intersect Saturn's path at a future time. These windows repeat with a regularity tied to the synodic period, the time it takes for Earth to catch up to Saturn in their relative positions. Because Saturn moves slowly and Earth moves faster, Earth returns to a similar alignment with Saturn, roughly once a little more than a year. The exact timing depends on orbital details, but the broad cadence is about yearly. This cadence matters for human time because it means a mission does not have to wait decades for a chance to depart, but it also means that missing a planned window can delay a mission by many months. Saturn's distance from Earth varies most strongly between two general configurations when Saturn and Earth are on the same side of the Sun and when they are on opposite sides. When Earth passes between the Sun and Saturn, Saturn is said to be at opposition. In that configuration, Saturn is visible all night and is closer to Earth than at other times. When Saturn is on the far side of the Sun from Earth, it is at conjunction, and it is farther away and near the Sun in the sky. For travel, opposition corresponds to a shorter straight-line separation, while conjunction corresponds to a longer separation. Yet interplanetary routes are not straight lines, and the best departure time depends on the chosen path. Even so, these configurations give a first range for distance. The minimum Earth-Saturn distance is on the order of billions of kilometers, and the maximum distance is roughly twice that, because the dominant factor is the size of Saturn's orbit compared with Earth's. In human terms, this means the destination is never close. It is always far beyond the outer edge of the inner solar system. Light, which is the fastest messenger, takes many minutes, and often more than an hour to travel between Earth and Saturn, depending on their positions. That fact will later be used to express the space between them in time units, but here it serves as a geometric anchor. Saturn is far enough that even light time is long, and the separation changes with orbital geometry. Saturn's place is also defined by its environment. It is a giant planet with a system of rings and many moons. The planet itself does not present a solid surface in the way Earth does. Its visible top is an atmosphere of hydrogen and helium with trace compounds structured by bands and storms and influenced by rapid rotation. This matters for travel time only indirectly, but it matters for what it means to reach Saturn. A mission to Saturn is not only a cruise to a point in space, it is an approach to a gravitational system. Saturn's gravity affects a spacecraft well before it arrives, and its moons can be used for gravitational assists or for targeted flybys. When a spacecraft enters Saturn's sphere of influence, it begins to orbit Saturn rather than the Sun, unless it performs a flyby and continues on a heliocentric path. Achieving orbit around Saturn requires a major reduction in speed relative to Saturn, which can be done by firing engines or by using atmospheric drag in an aerobraking maneuver, though the latter is difficult in Saturn's environment and is not commonly used. Many Saturn missions instead perform flybys or use long-duration orbital tours that rely on moon gravity assists after capture. These details are part of later sections, but they emphasize an important point about Saturn's location. Saturn is not a single target. It is a system whose gravitational field creates a region of navigation decisions. The travel time to reach Saturn can mean different endpoints. It can mean first crossing into the region where Saturn's gravity dominates. It can mean the moment of closest approach in a flyby. It can mean the moment of orbital insertion when the spacecraft becomes bound to Saturn. It can also mean arrival at a specific moon or ring plane. Each endpoint changes the time slightly because each requires different trajectory shaping. In this section, the target is defined as Saturn's orbital distance, and the need to intersect it with the understanding that the later definition of arrival will be made explicit when discussing real mission paths. The geometry of Saturn's orbit also matters in another way. Because the orbit is large, the sunlight reaching Saturn is much weaker than the sunlight reaching Earth. This affects spacecraft power systems because solar panels produce less power so far from the Sun. Many missions to Saturn use radioisotope power sources instead of relying solely on sunlight. This does not change cruise time directly, but it influences spacecraft design and operation over years, which is part of human time in an operational sense. The cold environment also affects thermal design and instrument performance. The long cruise includes long periods in cold, dim conditions. In the calm framing of the problem, Saturn's place is not only a far distance. It is a far distance in a region where sunlight is weak, temperatures are low, and communication delays are long. All of these factors shape what kind of spacecraft can make the journey and how it must be operated across years. Saturn's position relative to Earth and the Sun can be described in a simple moving map. Earth orbits close to the Sun. Saturn orbits far. Earth gains on Saturn in angular position each year because Earth moves faster. This creates repeating launch opportunities. The distance between Earth and Saturn ranges from a nearer configuration to a farther one, always within the scale of billions of kilometers. The route from Earth to Saturn is drawn not through empty straight-line space, but through the Sun's gravitational field, meaning the path is curved and the timing is set by orbital motion. A spacecraft that aims for Saturn must aim for where Saturn will be after months or years, not where it is at launch. This is a defining aspect of interplanetary travel that is especially clear for a distant planet with a long period. In human time, it implies that the journey is planned as a long arc with an arrival date that is chosen years in advance and adjusted with small corrections during flight. With Saturn placed in this moving solar system frame, the next step is to fix the scale of the map using the Earth-Sun distance as a measured unit. Once that unit is established, Saturn's orbit can be expressed in kilometers and in light time, and the travel time can be built from known trajectories that connect one orbit to another. To measure how long it takes to reach Saturn, the solar system's moving map must be given a fixed scale, and that scale begins with the Earth-Sun distance, because it is the base unit from which planetary distances are most cleanly derived. The Earth-Sun distance is not chosen for tradition alone. It is chosen because it is measurable, and because it is embedded in almost every step of interplanetary navigation. The average Earth-Sun distance is called the astronomical unit. Once it is fixed in kilometers, the orbital sizes of all planets can be expressed in the same language used for Earth travel, and then distances can be translated into time by combining them with spacecraft speeds. The astronomical unit is established historically through geometric methods and later refined with direct ranging. The geometry begins with the fact that Earth's orbit provides a baseline that can be used to infer distances to other bodies. When a planet is observed from different places on Earth at the same time, it shows a small parallax shift against background stars. When a planet is observed at different times from different points in Earth's orbit, the baseline is far larger, and the parallax effect can be used in more powerful ways. Rare events such as transits of Venus provide opportunities where the geometry is tightly constrained, letting observers infer the scale of the inner solar system. Over time, improved instruments and timing yield a better value of the astronomical unit. In the modern era, radar ranging makes the scale direct. A radio pulse is sent toward a planet such as Venus. The time delay of the returning echo is measured, and since the speed of light is known, the distance is calculated in kilometers. This method ties the solar system's scale to a physical constant and reduces uncertainty dramatically. Whether derived from transits, orbital dynamics, or radar, the outcome converges. The astronomical unit is about 150 million kilometers. That number is important not because it must be memorized, but because it becomes a mental step size for solar system distances. 1 astronomical unit is the distance between Earth and the Sun. Saturn's orbit is about 9.5 astronomical units from the Sun on average. That means Saturn's average distance from the Sun is roughly 9.5 times 150 million kilometres, or roughly 1.5 billion kilometres. Because Saturn's orbit is not a perfect circle, the distance varies somewhat over its year, but the variation is small compared with the total. Earth's own orbit varies slightly too. For travel time, the more important variation is the changing distance between Earth and Saturn as they move around the Sun. When Earth and Saturn are on the same side of the Sun near opposition, the straight line separation can be on the order of 8.5 astronomical units, which corresponds to roughly 1.25 to 1.33 billion kilometres. When they are on opposite sides of the Sun near conjunction, the separation can approach 10.5 astronomical units, roughly 1.5 to 1.2 billion kilometres. These are broad figures because the exact values depend on the specific orbital positions and on the slight ellipticity of the orbits. But they are sufficient to show that even in the near configuration, Saturn is more than 1 billion kilometres away, and in the far configuration it is substantially farther. Once the astronomical unit is known, another useful measure becomes available immediately: light time. Light crosses 1 astronomical unit in about 8 minutes. This value is not arbitrary. It comes from dividing 150 million kilometres by the speed of light, which is about 300,000 kilometres per second. 8 minutes is a human unit that can be felt. It is the time for a short walk, the time to boil water, the time to read a few pages. When the solar system is expressed in light time, its scale becomes more concrete. Saturn, at around 9.5 astronomical units from the Sun, is about 9.5 times 8 minutes in light time, which is little more than 1 hour. The radio signal time between Earth and Saturn depends on their separation, so it ranges from a bit more than an hour to closer to an hour and a half, with the exact time changing day by day. This is why spacecraft at Saturn cannot be controlled in real time from Earth. A command takes a long time to arrive, and confirmation takes equally long to return. Even before travel time is discussed, this signal delay shows what distance means in human time. It is a fixed translation that depends on light speed. Travel time is slower by orders of magnitude because spacecraft do not travel at light speed. Now the astronomical unit can also be used to describe spacecraft speeds in a way that links to human time. Earth's orbital speed is roughly 30 kilometers per second. A spacecraft leaving Earth already shares that heliocentric motion. When a spacecraft is sent outward, it must change its heliocentric energy so that its orbit reaches farther from the Sun. The energy change is applied through rocket burns or through gravitational assists, but the result can be described as a change in velocity. Typical interplanetary cruise speeds relative to the Sun are on the order of tens of kilometers per second. These values sound large when compared with aircraft speeds, but they are still very small compared with the speed of light. At 10 kilometers per second, a spacecraft covers about 860,000 kilometers in one day, because a day has 86,400 seconds, and 10 kilometers each second yields that product. At 20 kilometers per second, it covers about 1,700,000 kilometers per day. These daily distances are large compared with Earth travel, but small compared with the billions of kilometers to Saturn. A simple division shows the scale. If the straight line distance were 1.5 billion kilometers, and a spacecraft could somehow travel at a constant 20 kilometers per second in a straight line, it would take about 75 million seconds, which is about 865 days, a little under 2.5 years. At 10 kilometers per second, the time would be about twice that, around 5 years. These crude calculations are not actual mission times, because real trajectories are curved and spacecraft do not travel straight at constant speed from Earth to Saturn. They must climb out of the Sun's gravity well, which changes their speed as they move outward. They also must meet Saturn's moving position, which sets the timing. Still, the calculation is useful because it gives a first human time range based on plausible speeds, a few years, not a few months, and not a few decades for robotic missions with typical propulsion and with efficient trajectories. The reason the straight-line constant speed estimate is not the actual route is that orbital mechanics trade speed for energy in a curved path. A spacecraft leaving Earth on a transfer to Saturn will typically have its highest heliocentric speed near Earth's orbit, where it receives the main push, and then it will slow as it climbs outward, because the Sun's gravity converts kinetic energy into gravitational potential energy. By the time it reaches Saturn's orbit, its heliocentric speed is lower. This is not failure. It is the expected behavior of a ballistic arc. The transfer time is therefore not set simply by dividing a fixed distance by an average speed. It is set by the shape of the transfer orbit and by the laws that connect orbital size to orbital period. This connection will be the focus of later sections. For now, the astronomical unit provides the scale and provides a first translation into both kilometers and light time. The phrase measured in human time begins to take shape as a set of conversions. 1 astronomical unit is 150 million kilometers and about 8 minutes of light time. Saturn's orbit is about 9.5 astronomical units from the Sun, and Earth's is 1. The Earth-Saturn separation is therefore always in the range of many astronomical units, and corresponds to more than an hour of light time. This alone sets expectations for communication delay. For travel time, typical spacecraft cruise speeds mean that each day covers less than 2 million kilometers, even at high tens of kilometers per second. Reaching a destination more than 1 billion kilometers away therefore requires hundreds of days at minimum, and more commonly years when the curved path and energy changes are taken into account. The astronomical unit also provides a common language for mission planning. When navigation teams describe trajectories, they work in a heliocentric frame where positions and velocities are related to the Sun, and distances are naturally expressed in astronomical units. When the public hears about the journey, it is often expressed in kilometers and in years. The bridge between those descriptions is the astronomical unit. It ties the solar system's geometry to human units. It also removes ambiguity. Without a fixed Earth-Sun distance, 9.5 times Earth's orbit remains an abstract ratio. With the astronomical unit, it becomes a distance with an actual number. The next step is to use this fixed scale to describe how the distance between Earth and Saturn changes over time, and how the changing geometry creates a range of possible travel distances. That range will then be connected to the kinds of paths a spacecraft can take, showing why mission times cluster around certain values, rather than spanning all possible durations. With the astronomical unit fixing the solar system's scale in kilometers, and in light time the outer region becomes the moving gap between Earth and Saturn, because that gap is not constant, and because human travel time depends on the distance that must actually be covered along a real trajectory. Earth and Saturn are both in motion around the Sun. Earth completes its orbit in 1 year. Saturn completes its orbit in close to 30 years. This difference means that Earth gains on Saturn in angular position year by year. The geometry of the two orbits produces repeating patterns of closer and farther separations, and it produces repeating launch opportunities. The key idea is that a spacecraft does not chase a stationary target. It leaves Earth at a particular time, enters a heliocentric trajectory, and arrives at a point in space where Saturn will be after months or years. The journey time is therefore tied to 2 clocks at once, the clock of the spacecraft's transfer path, and the clock of Saturn's motion along its orbit. To understand travel time in human units, it helps to describe what distance to Saturn means at different moments. If Earth and Saturn are on the same side of the Sun, the straight-line separation can be near its minimum. This is the general situation around opposition, when Saturn is opposite the Sun in Earth's sky. At opposition, Earth lies between the Sun and Saturn, so the line from Earth to Saturn extends outward from the Sun. In this arrangement, the separation is roughly Saturn's orbital radius minus Earth's orbital radius, which is around 8.5 astronomical units. If the astronomical unit is about 150 million kilometers, then 8.5 astronomical units is on the order of 1.25 billion kilometers. If Earth and Saturn are on opposite sides of the Sun, the straight line separation approaches the sum of their orbital radii, which is around 10.5 astronomical units, on the order of 1.5 to 1 2/3 billion kilometers. These numbers are not fixed because the orbits are slightly elliptical, and because opposition and conjunction are not perfect point events in a smooth circle. But the range is stable enough to support the main inference. The straight line distance varies by hundreds of millions of kilometers over the cycle. In human time, that variation is significant because at typical spacecraft speeds, hundreds of millions of kilometers correspond to many months of travel. However, the straight line separation is not the distance a spacecraft actually travels, because spacecraft follow curved paths governed by gravity. Even so, the changing straight line separation is a useful first indicator of the changing scale of the problem. A more relevant measure is the heliocentric geometry of a transfer. A spacecraft begins near Earth's orbit at about 1 astronomical unit from the Sun. It must end near Saturn's orbit at about 9.5 astronomical units. That change in orbital radius is the essential distance change. In an energy-efficient transfer, the spacecraft does not travel along a simple radial line outward. Instead, it enters an elliptical orbit around the Sun, whose closest point, the perihelion, is near Earth's orbit, and whose farthest point, the aphelion, is near Saturn's orbit. This elliptical path means the spacecraft travels a long arc around the Sun while it moves outward. The length of that arc depends on the transfer orbit's shape, and on how fast Saturn moves during the travel. The spacecraft's travel time is not just a function of distance, but also of orbital period. In the simplest, efficient transfer, the travel time is roughly half the period of the transfer ellipse. Because the transfer ellipse is much larger than Earth's orbit, its period is longer than 1 year, and half that period can be several years. This is why efficient travel to Saturn is commonly measured in years. The moving geometry also affects the choice of arrival. If the spacecraft is to arrive at Saturn when Saturn is at a certain point in its orbit, the departure must occur when Earth is at a point that leads to that intersection. This is the reason for launch windows. A window exists when given a chosen transfer time, Earth's position at departure and Saturn's position at arrival match the geometry of the transfer orbit. If the transfer time is longer, the alignment requirements change because Saturn has more time to move. If the transfer time is shorter, the alignment requirements change because Saturn moves less. Thus, travel time and launch date are linked. For human time, this means that how long it takes is partly a design choice, not only an unavoidable fact. A mission can choose to take a longer, lower energy path that requires less fuel but more time, or a shorter, higher energy path that requires more fuel but less time. The changing Earth-Saturn geometry then determines when each of those choices is possible. The range of distances and times can be made more concrete by considering how fast the spacecraft can move in terms of the Sun-centered frame. After leaving Earth, the spacecraft is in orbit around the Sun. Its heliocentric speed near Earth's orbit is comparable to Earth's orbital speed, about 30 kilometers per second plus or minus the effect of the launch and the departure from Earth. When the spacecraft is pushed outward, its orbit has a larger size and it will have a different speed at different distances. Near the Sun it moves faster. Far from the Sun it moves slower. This is the behavior of an ellipse in a gravitational field. Thus, even if the spacecraft begins with a high speed relative to the Sun, it will slow as it climbs outward towards Saturn's distance. In practical terms, this means that the early part of the journey covers distance more quickly, and the later part covers distance more slowly, not because the spacecraft is tired, but because gravitational energy is being traded for altitude in the Sun's potential well. The total travel time depends on the overall energy of the orbit, which determines its size and period. The changing distance between Earth and Saturn also affects communication delay in a way that is simple and steady. Because radio signals travel at the speed of light, the one-way light time between Earth and Saturn is roughly the Earth-Saturn separation divided by the speed of light. When the planets are closer, the delay is shorter. When they are farther, the delay is longer. At the nearer end, the one-way delay is a bit more than an hour. At the farther end, it can be closer to an hour and a half. This changing delay matters operationally because it sets how long a mission team must wait to confirm a command or to receive data. It also matters as a measure of distance in human time because it is a direct translation that does not depend on propulsion. It is the minimum possible time for information to cross the gap. Travel time is always much longer. The difference between light time and travel time is itself a marker of how the solar system's vastness changes with distance. At the Moon, the difference is a few days of travel versus a little more than a second of light time. At Saturn, the difference is years of travel versus more than an hour of light time. Both are large ratios, but the absolute times become more noticeable. Another aspect of moving distance is that Saturn's orbit sets a broad seasonal pattern for launch opportunities, because Earth's position relative to Saturn repeats approximately yearly, but not exactly on the same calendar date. The reason is that Earth's orbit and Saturn's orbit do not have a simple integer ratio of periods. After one Earth year, Saturn has moved a small fraction along its orbit, so the exact alignment for a given trajectory occurs a bit later each year, creating a slow drift. Mission planners account for this when selecting launch dates. They also account for constraints on spacecraft orientation, solar power thermal conditions, and communication geometry with Earth. These constraints can narrow a window from weeks to days. For human time, this matters because it adds a weighting component that is not travel, but is part of the timeline of reaching Saturn. A mission might be ready to fly, but must wait months for the correct alignment. Yet once launched, the cruise time dominates. The moving distance between Earth and Saturn also affects the way travel time is described to the public. If someone asks for the distance to Saturn, it is correct to answer with a range rather than a single number because the planets move. If someone asks how long it would take, it is likewise correct to give a range for typical mission profiles, rather than a single number, because different trajectories and different launch dates produce different times. A low-energy transfer might take around 6 to 7 years. A higher energy transfer could take less. A gravity assist route that visits other planets can take longer or shorter, depending on the sequence and the constraints. The existence of this variety does not mean the problem is open-ended. The physics of orbital transfer tends to cluster viable mission times into a narrow band of years, because the energy required to reduce time sharply grows quickly, and because the geometry of planetary orbit sets limited opportunities. In this section, the emphasis remains on the moving distance and its consequences. The destination is always far, in the range of billions of kilometers. The exact distance changes with orbital alignment. The straight-line gap changes by hundreds of millions of kilometers, which corresponds to months of travel at typical spacecraft speeds. Efficient routes are curved and are tied to orbital periods, meaning that travel time is naturally measured in years. The spacecraft must be aimed not at Saturn's present location, but at its future location, binding departure time to arrival time. Communication delay is measured in more than an hour one way, reinforcing the scale in human time. With this moving geometry established, the next step is to compare the human intuition of a straight path with the actual curved paths used in spaceflight, showing why distance to Saturn is not the same as distance travelled, and why the shortest distance is not the fastest or the most efficient. A human mind tends to picture travel as a straight line from a starting point to a destination, because that is how movement works on a road or across open water, when gravity and rotation can be ignored at the scale of the trip. In space, that straight-line intuition quickly becomes misleading, especially for a journey from Earth to Saturn. The outer region here is the difference between the shortest geometric separation and the path a spacecraft actually follows, because the difference explains why travel time is measured in years, and why faster is not simply a matter of pointing outward and accelerating. The straight-line distance between Earth and Saturn at a given moment is the length of the chord between 2 points on different orbits. It can be expressed in kilometers and translated into light time. Yet a spacecraft launched from Earth does not simply travel along that chord. It begins inside Earth's gravity well, then enters a heliocentric orbit around the Sun. Once it is in heliocentric space, the Sun's gravity dominates. In this environment, a spacecraft that does nothing will follow a natural path called a ballistic trajectory, determined by its current position and velocity. Changing that path requires thrust, which changes velocity. Because fuel is limited, spacecraft trajectories are designed to use gravity as the main guide rather than fighting it. This means the path to Saturn is typically a curved arc around the Sun, not a straight line, and the distance travelled along the arc is longer than the instantaneous straight-line separation between Earth and Saturn. The extra distance is not wasted distance. It is the shape required to rise from Earth's orbit to Saturn's orbit while staying in a stable orbit around the Sun. In everyday terms, a spacecraft is not crossing empty space, as if it were flat. It is moving within a gravitational landscape where free motion is orbital. The most common minimal fuel way to move from one circular orbit to another is to use an elliptical transfer orbit that touches the departure orbit at one point and touches the destination orbit at another. This is the essence of a Hohmann transfer, which will be described later in detail. Here the important point is that the transfer is an orbit around the Sun, and its timing is tied to orbital periods. A straight-line path would require continuous acceleration to keep the spacecraft from falling into a different orbit around the Sun or from missing Saturn's path. Continuous acceleration over years is not a typical capability of current spacecraft, which use brief engine burns rather than sustained high thrust. Even if continuous thrust were available, the fuel requirement would be enormous, and the design would shift into a different category. So the curved path is not only the result of tradition, it is the result of constraints. The spacecraft follows a path that the Sun's gravity will naturally support after a few carefully timed changes in velocity. This is why the shortest geometric distance is not the same as the practical travel distance. There is also a second reason straight lines mislead Saturn moves. If a spacecraft were to aim at Saturn's current position and travel in a straight line, Saturn would not be there when the spacecraft arrived months or years later. The correct aim point is ahead of Saturn, along its orbit at the location Saturn will occupy at arrival. This is like throwing a ball to a moving runner. The throw must lead the runner, not chase the runner's present spot. In the solar system, the lead is large because of the long travel time. Saturn moves along its orbit during the cruise, and the spacecraft's path must intersect Saturn's future location in both space and time. This requirement makes the trajectory a timed intersection between two moving bodies, not a simple point-to-point line. The third reason is that speed in space is not a single number. A spacecraft has different speeds relative to Earth, relative to Saturn, and relative to the Sun. In planning a transfer, the heliocentric speed is central because it determines the orbit around the Sun. When a spacecraft leaves Earth, it already has Earth's heliocentric speed because it shares Earth's motion. It then adds or subtracts from that speed through a departure burn. This changes the shape of its heliocentric orbit. As it travels outward, its heliocentric speed decreases because it is climbing away from the Sun in gravitational terms. By the time it reaches Saturn's distance, it is moving more slowly around the Sun than it did near Earth. Saturn itself moves around the Sun at a speed set by its orbit slower than Earth. The spacecraft's speed relative to Saturn at arrival depends on the shape of the transfer and on the arrival geometry. If the spacecraft approaches Saturn on a path that is faster than Saturn's own orbital motion, it will have a high relative speed, which is suitable for a fast flyby, but makes capture into orbit difficult. If the spacecraft approaches with a relative speed that is closer to Saturn's capture, is easier, but the transfer may have taken longer or required different energy. Thus faster is not simply reaching Saturn sooner. It is also arriving with a particular relative speed which determines what can be done upon arrival. A mission that wishes to enter orbit around Saturn must remove enough relative speed to become bound. That removal requires fuel or clever use of moon flybys after a partial capture. Missions that only wish to fly past Saturn can accept higher arrival speeds. This affects the time because higher energy transfers tend to be shorter, but they come with higher relative speed at Saturn. The trade is between time and the ability to slow down at the destination. The path geometry also influences how close the spacecraft must pass to the Sun and to other planets. Some trajectories to Saturn take a direct outward arc that stays between Earth's orbit and Saturn's orbit. Others swing inward toward the Sun, first gaining speed by falling deeper into the Sun's gravity well, and then swing outward. This can reduce travel time for a given propulsion capability, because the spacecraft can gain heliocentric speed by descending closer to the Sun and then climbing outward. Yet such trajectories can impose thermal constraints and may require additional energy changes. Other trajectories use gravity assists. A gravity assist is a maneuver where a spacecraft passes near a planet and exchanges momentum with it changing its heliocentric velocity without using much fuel. The planet's motion around the Sun provides the energy source. In the planet's frame, the spacecraft swings around and leaves with the same speed it had when it arrived, but in the Sun's frame the direction and sometimes the magnitude of its velocity changes, leading to a net gain or loss of heliocentric energy. Gravity assists allow missions to reach Saturn with less fuel or with different timing than would be possible with a direct transfer alone. However, gravity assists add path length and add waiting time, because the spacecraft must meet the assisting planet at a specific time and location. A route that goes to Venus, then Earth, then Jupiter, and then Saturn can be efficient in fuel, but it can take longer than a more direct route. It can also be the only feasible route for a spacecraft with limited launch energy. Thus, the distance travelled can be very large even though the destination is Saturn, because the path includes loops and swings shaped by gravitational encounters. In human time, these loops translate into years added or redistributed. The mission does not simply travel outward. It follows a planned schedule of planetary meetings. Each meeting is a timed event. Between them are cruise phases. The total travel time is the sum of these phases and the weighting implied by the geometry of each encounter. The difference between straight-line distance and trajectory distance can be described plainly. If the straight-line distance from Earth to Saturn is around 1.5 billion kilometers, at a particular alignment the spacecraft may travel several billion kilometers along its heliocentric arc before reaching Saturn, depending on the trajectory. This does not mean the spacecraft is inefficient. It means the natural orbital paths in a gravity-dominated system are curved, and the spacecraft is conserving fuel by following those paths. The question of how long it takes is therefore best answered not by a straight-line division, but by describing the class of trajectory. A low-energy transfer will take longer because it follows an orbit with a longer period. A higher-energy transfer will take shorter because it follows a faster, more energetic path, but it may require more fuel and result in a higher arrival speed. A gravity assist trajectory may reduce fuel needs, but can increase duration because it involves additional travel and alignment constraints. In human time, this means the journey to Saturn is not a single fixed duration. It is a range of durations tied to path choices and constraints, with typical values of several years for robotic missions. This section stays with the geometric and conceptual distinction. The shortest distance is not the route. The route is an orbit around the Sun designed to intersect Saturn's moving position. Speeds must be described relative to frames, and arrival speed matters as much as cruise speed. Gravity assists can substitute for fuel but can add time. With these distinctions clear, the next step is to describe gravity as the guiding principle that makes these curved paths predictable and efficient, showing how energy and orbital mechanics shape the trade between time and fuel on the way to Saturn. Gravity is the quiet rule that makes long-distance travel in the solar system possible at all, because it turns motion into predictable curves instead of chaotic drifting. The outer region here is the Sun's gravitational field as the main environment for the journey to Saturn, because every practical route to Saturn is shaped first by the Sun and only second by the planets. In a sun-centered view, a spacecraft is a small mass moving in the field of a much larger mass. If no thrust is applied, the spacecraft follows a conic section, an ellipse if it is bound to the Sun, a parabola, or hyperbola if it has enough energy to escape. For a mission to Saturn, the spacecraft remains bound to the Sun for most of the cruise, following an ellipse whose closest approach to the Sun is near Earth's orbit, and whose farthest reach approaches Saturn's orbit. The efficiency of this approach comes from a simple fact: it is easier to change a spacecraft's orbit with a small push than to propel it continuously in a straight line over billions of kilometers. The reason is that a well-timed change in velocity alters the entire future path. A brief burn can reshape an orbit for years. This is the foundation of interplanetary navigation. It also explains why the question how long is inseparable from the question what orbit. In this environment, travel time is tied to orbital period. An orbit is not only a path, it is a schedule. The schedule depends on the size of the orbit. Larger orbits take longer to complete because the average distance from the Sun is greater and the gravitational pull is weaker, leading to slower motion. This relationship is captured in Kepler's third law, which states that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. The same law applies to spacecraft orbits around the Sun. If a transfer orbit has a semi-major axis larger than Earth's, its period will be longer than 1 year. If a transfer orbit is designed to reach Saturn's distance, its period will be long enough that half of it, the time to go from perihelion to aphelion, will be measured in years. Thus, gravity makes it possible to reach Saturn without continuous thrust, but it also sets a natural timescale for low-energy travel. The spacecraft is in a sense taking part in the solar system's own clockwork. The journey is not a straight push through space. It is an insertion into a new solar orbit, and then a gradual rise outward along that orbit, until the spacecraft reaches the same orbital distance as Saturn. Gravity also defines the trade between time and fuel. Fuel is used to change velocity. In orbital mechanics, the key quantity is delta V, the total change in velocity a spacecraft must produce through its engines. Delta V is costly because it consumes propellant. For chemical rockets, propellant mass grows rapidly with required delta V. This means that making a transfer much faster by increasing delta V can quickly become impractical for a given launch vehicle and spacecraft mass. Therefore, missions often choose trajectories that minimize delta V, even if they take longer. This is not because mission planners prefer waiting. It is because the physics of propulsion makes time a cheaper resource than fuel. Gravity provides the mechanism that allows this trade. By accepting a longer travel time, the spacecraft can use a lower energy orbit that requires smaller burns. The most common efficient method for changing from one circular orbit to another is a two-burn strategy. The first burn changes the spacecraft from the departure circular orbit to an elliptical transfer orbit. The second burn circularizes the orbit at the destination distance, if the goal is to match the destination's orbit. For Saturn, that second burn would be associated with matching the spacecraft's heliocentric orbit to Saturn's heliocentric orbit, and then additional steps would be needed to become bound to Saturn itself. This two-burn idea is the seed of the Hohmann transfer described later. In this section, the focus is on the gravitational logic behind it. A small push at the right time changes the orbit, and the orbit carries the spacecraft outward. The spacecraft's speed changes along the way without any additional thrust because energy is conserved in the gravitational field. Near Earth's orbit, where the spacecraft begins its heliocentric speed, is relatively high. As it moves outward, its speed decreases. This decrease can be predicted precisely. It is not a matter of friction or loss because space is nearly empty. It is the conversion between kinetic energy and gravitational potential energy. When the spacecraft is near the Sun, it is deep in the gravitational well and moves faster. When it is far from the Sun, it is higher in the well and moves slower. This behavior has a direct effect on travel time. A spacecraft covers large distances quickly early in the transfer and more slowly near the far end. The cruise is therefore not uniform. Yet the overall time is still dominated by the orbital period relationship, not by small variations in speed. Gravity also shapes the way Saturn itself is encountered. Saturn has its own gravitational field, and as the spacecraft approaches, Saturn's gravity begins to dominate locally. There is a region around Saturn where the gravitational pull of Saturn on the spacecraft becomes stronger than the differential pull from the Sun. This region is often described as the sphere of influence, or more precisely in a dynamical sense, the Hill sphere. The Hill sphere defines the space around Saturn, where satellites can remain in orbit around Saturn, while still orbiting the Sun as part of the larger system. When a spacecraft crosses into this region on an approach trajectory, its path relative to Saturn can be treated as a hyperbolic flyby, unless it performs a capture maneuver. Gravity again turns the problem into geometry. Relative to Saturn, an incoming spacecraft follows a hyperbola if it is not captured. The shape of that hyperbola depends on the approach speed and the closest approach distance. If the spacecraft wishes to be captured into orbit around Saturn, it must reduce its speed relative to Saturn enough that the trajectory becomes bound. That reduction is done by firing engines near closest approach, where the effect of a given burn on the orbit around Saturn is strongest. This is another general principle. Burns performed deep in a gravitational well are more effective for changing the spacecraft's energy relative to that body. This is called the Oberth effect. Near a planet, a burn can change the spacecraft's trajectory more than the same burn performed far away, because the spacecraft's speed relative to the planet is higher. This effect is used in some mission designs, and it also explains why deep space maneuvers are scheduled at particular times. For a Saturn mission, the major propulsive events are typically at launch, perhaps during cruise as small corrections and at arrival if capture is needed. The rest is coasting under gravity. The gravitational environment also makes it possible to gain energy without spending propellant through gravity assists. A gravity assist is a controlled flyby of a planet that changes the spacecraft's heliocentric velocity. The planet's gravity bends the spacecraft's path. Because the planet itself is moving around the Sun, the bending can result in a net change in the spacecraft's speed and direction in the Sun's frame. From the planet's perspective, the spacecraft's speed far from the planet before and after the flyby is about the same, but its direction changes. When transformed back to the Sun's frame, the spacecraft can gain or lose heliocentric energy. This technique is especially useful for reaching Saturn because Saturn is far and reaching it directly with a heavy spacecraft can demand high launch energy. A mission can use flybys of inner planets Earth or Jupiter to reshape its solar orbit gradually. Each flyby is like a free burn provided by gravity. But the free burn comes with timing constraints. the spacecraft must arrive at the assisting planet at the right time and altitude, and that requirement can lengthen the overall trip. Here again the theme is trade. Gravity can save fuel, but it can cost time. In human terms, this is a choice between carrying more propellant for a direct route, or accepting a longer cruise with planned planetary meetings. The Sun's gravity also defines a practical limit on how quickly a spacecraft can move outward without enormous energy. To go outward fast, the spacecraft's heliocentric orbit must be highly energetic, approaching a trajectory that is not strongly bound. This implies high speeds near Earth and high departure energy from Earth. High departure energy means a powerful launch vehicle, or a light spacecraft, or both. If those are not available, gravity-assisted routes become attractive. Thus, the journey time to Saturn is not just a distance problem, it is an energy and gravity problem expressed in human time. Efficient paths take years because they are tied to the natural timescales of large solar orbits. Faster paths require more energy and often arrive with higher relative speeds that complicate capture. Gravity assists offer intermediate options. This section therefore establishes gravity as the main guide that makes the trip predictable and explains the structure of time in the journey. The spacecraft's cruise is a controlled fall and climb in the Sun's gravitational field with occasional small pushes. The time is measured in years because the relevant orbits have multi-year periods. The next step is to describe the specific low-energy route that is most often used as a benchmark, the Hohmann transfer, and to translate its orbital timing into human time to give a clear baseline for how long reaching Saturn can take when fuel is conserved. A practical baseline for how long it takes to reach Saturn is the low-energy transfer that orbital mechanics naturally suggests when moving from a smaller circular orbit to a larger one, the Hohmann transfer. This route is not a guess. It is a solution that minimizes the total change in velocity needed for a transfer between two coplanar circular orbits when only two brief engine burns are used, one to depart and one to match the destination orbit. The Hohmann transfer is therefore a useful reference even when real missions choose more complex paths, because it defines the slow, fuel-efficient end of the trade between time and energy. In a sun-centered view, Earth travels around the Sun at about 1 astronomical unit. Saturn travels around the Sun at about 9.5 astronomical units. A Hohmann transfer from Earth's orbit to Saturn's orbit is an ellipse around the Sun whose perihelion lies at Earth's orbital radius, and whose aphelion lies at Saturn's orbital radius. The semi-major axis of this ellipse is the average of the perihelion and aphelion distances. In plain terms, it is about the midpoint between 1 astronomical unit and 9.5 astronomical units, which is about 5.25 astronomical units. The time to travel from perihelion to aphelion on this ellipse is half the orbital period of the ellipse. Kepler's third law links the orbital period to the semi-major axis. For objects orbiting the Sun, the period in years is proportional to the semi-major axis in astronomical units raised to the 3/2 power. That means if the semi-major axis is larger than 1, the period grows faster than linearly. For a semi-major axis of about 5.25, the period is about the square root of 5.25 cubed. 5.25 cubed is a number a little above 140. The square root of that is a number close to 12. So the full period of the transfer ellipse is on the order of 12 years. Half of that is on the order of 6 years. This is the key baseline result. A Hohmann transfer from Earth's orbit to Saturn's orbit takes roughly 6 years of flight time, measured from the time the spacecraft leaves Earth's orbit to the time it reaches Saturn's orbital distance. The exact value depends on the exact orbital radii used, the slight eccentricities, and the specific mission design, but the order is stable. It is not months. It is years. It is not several decades. It is a span that fits within a human career and within the lifespan of a well-designed spacecraft. This is why many Saturn missions have cruise times of several years, and why 6 years appears repeatedly as a rough figure in discussions of low-energy travel. Yet it is important to keep the meaning precise. The Hohmann transfer time is the time to reach Saturn's orbital distance, not necessarily the time to be captured by Saturn. To be captured, the spacecraft must also match Saturn's position along its orbit at the correct moment, and it must reduce its speed relative to Saturn. In a pure Hohmann transfer between circular orbits, the second burn at aphelion would circularize the heliocentric orbit at Saturn's distance, matching Saturn's heliocentric speed. In reality, the spacecraft does not need to become a planet. It needs to encounter Saturn at the right place. Many missions approach Saturn on a heliocentric trajectory that intersects Saturn's path and then use a Saturn orbit insertion burn to become bound to Saturn. That burn is performed relative to Saturn, not relative to the Sun, and it does not necessarily produce a heliocentric circular orbit at Saturn's distance. It produces a Saturn-centered orbit. The Hohmann transfer remains useful because it sets the timescale of the outward cruise. The encounter geometry adds additional constraints but usually does not change the basic multi-year scale. The alignment required for a Hohmann transfer can also be described in simple terms. Because the spacecraft will take about 6 years to reach Saturn's distance, Saturn will move along its orbit during those 6 years. Saturn completes an orbit in about 30 years, so in 6 years it moves about 1/5 of a full circle, on the order of 70 degrees. Earth during the same time completes 6 full orbits. This means that at launch Saturn cannot be directly ahead in the sky, in the way a straight-line intuition might suggest. Saturn must be in a position such that after 6 years of travel along the transfer ellipse, the spacecraft arrives at the location where Saturn will be. This sets a phase angle, a specific angular separation between Earth and Saturn at launch. The existence of a phase angle requirement explains why launch windows are periodic. As Earth moves faster, it cycles through possible alignments with Saturn regularly, and the correct phase angle recurs. For Saturn, this recurrence is on the order of a year because Earth gains on Saturn steadily. In human time, this means that a mission designed around a Hohmann-like transfer does not wait decades for alignment, but it still must choose an appropriate month and year. Missing the window can mean waiting a year or more for similar geometry. The Hohmann transfer is also linked to the energy required at departure. The spacecraft must be given enough heliocentric energy to enter the transfer ellipse. Relative to Earth, this requires leaving Earth with an excess speed beyond what is needed to just escape Earth's gravity. That excess speed is called hyperbolic excess speed, and it sets the needed launch energy. For Saturn, the required departure energy for a pure Hohmann is significant, but not extreme compared with even farther destinations. Still, because Earth's gravity well must be climbed, and because the spacecraft must add to Earth's heliocentric speed, the launch vehicle must provide a substantial boost. This is why Saturn missions are often large and rely on powerful rockets or on gravity assist to reduce the required launch energy. The Hohmann transfer provides the minimum delta-v between orbits, but does not necessarily minimize launch energy in a real Earth departure scenario, because the spacecraft begins in Earth orbit rather than at rest in the Sun's frame. Nevertheless, it remains the conceptual baseline. It says that if fuel efficiency is the priority, and if a direct two-burn transfer is used, the travel time will be around 6 years. This number can now be translated into human calendar terms. 6 years is about 6 cycles of seasons on Earth, 6 sets of birthdays, 6 school years for a child, and 6 annual maintenance cycles for the teams who support a mission. In mission operations, it is long enough for staff to change roles and for ground systems to be upgraded. It is also short enough that a mission can be planned with a stable set of assumptions. A 6-year cruise is not a brief event, but it is manageable. The spacecraft itself must survive in space for that long, meaning its power source, thermal control and communication systems must be reliable over years. Cruise phases often include long quiet periods. Instruments may be turned off to conserve power and to reduce wear. The spacecraft may be placed in a slow spin for stability. Periodic checkouts are scheduled and trajectory correction maneuvers are performed as needed to refine the aim. These correction burns are small compared with the main departure and arrival burns, but they are essential for accuracy. Over 6 years, small initial errors would compound into large missed distances without correction, because Saturn is a small target in a vast space. In this way, a multi-year transfer also becomes a multi-year process of gentle steering, guided by radio tracking and precise navigation. The Hohmann transfer also implies a certain arrival speed relative to Saturn in the Sun's frame. At Saturn's distance, the spacecraft's heliocentric speed on the transfer ellipse is lower than Earth's heliocentric speed, and it is close to Saturn's heliocentric speed, because the ellipse's aphelion is at Saturn's radius. This helps in principle, because a closer match to Saturn's heliocentric speed can reduce relative approach speed. But in practice, the approach speed relative to Saturn still depends on the exact encounter geometry and on whether the spacecraft arrives inside or outside Saturn's orbit plane and how the trajectory intersects Saturn's path. Even with a Hohmann-like transfer, an orbit insertion burn at Saturn is usually required if the mission intends to orbit rather than fly past. The need for insertion burn and the size of that burn are part of the total mission design trade, but the cruise time remains dominated by the transfer orbit period. Thus, Section 7 provides a clear baseline answer. In human time, the low-energy direct transfer to Saturn's orbital distance takes about 6 years. This is not the only possible time, but it is a reference point that explains why the phrase several years is the most honest first description of Saturn travel. The next step is to ground this baseline in the speeds that spacecraft actually achieve, and to translate those speeds into human experience, showing how tens of kilometers per second in space becomes years of travel, when the path is an orbit rather than a straight line. After the Hohmann transfer provides a baseline of roughly 6 years for a fuel-efficient route to Saturn's distance, the outer region becomes the speeds that spacecraft can actually achieve, and how those speeds translate into human time without relying on intuition that comes from roads and airplanes. Spacecraft speeds are often stated in kilometers per second, a unit that can sound abstract because human life is normally paced in kilometers per hour. A simple conversion helps ground the scale. 1 kilometer per second is 3,600 kilometers per hour. Even a modest spacecraft speed of 10 kilometers per second corresponds to 36,000 kilometers per hour, far faster than any airplane. A speed of 20 kilometers per second corresponds to 72,000 kilometers per hour. These numbers establish that interplanetary travel involves speeds that are already extraordinary in everyday terms, yet the distances involved are so vast that these speeds still yield travel times measured in years. This is the core translation that must be handled carefully. A spacecraft on a Saturn trajectory does not hold a constant speed, relative to the Sun or relative to Earth. Its speed changes as it moves outward, and it depends on the energy of the trajectory. Still, typical cruise speeds relative to the Sun are on the order of tens of kilometers per second near the inner solar system, and lower in the outer solar system. Typical speeds relative to Earth after departure, when measured as hyperbolic excess speed, are also often several kilometers per second. These values may vary widely depending on mission design, launch vehicle capability, and gravity assists. To keep the translation in human time steady, it is useful to focus on what these speeds mean in daily and yearly distances. A spacecraft traveling at 10 kilometers per second covers about 860,000 kilometers in one day. At 20 kilometers per second, it covers about 1,700,000 kilometers in one day. In 1 year of steady travel at 20 kilometers per second, the spacecraft would cover about 630 million kilometers. Yet a Saturn journey requires more than 1 billion kilometers of outward reach and follows a curved orbit. That is why a few years is a natural result. Even under an idealized assumption of constant high speed and straight travel, the time would not be measured in weeks. It would be measured in years. When the realistic slowdown in the outer solar system and the longer orbital path are included, the baseline of roughly 6 years for a low-energy transfer begins to feel consistent with these speed-to-time conversions. Human time also includes the acceleration phase, the part of the journey when most of the speed change occurs. For chemical rockets, most acceleration happens in minutes during launch, and in short burns of minutes to hours for deep space maneuvers. This is unlike a car or airplane which can adjust speed continuously. A spacecraft's speed is therefore largely set early, and then gravity reshapes how that speed turns into distance over time. The launch provides a large impulse that lifts the spacecraft from Earth and shapes its heliocentric orbit. Once in heliocentric space, the spacecraft is in free fall around the Sun, and its speed changes because of gravity rather than because of continued thrust. This makes the journey feel paradoxical in everyday terms. The spacecraft can be moving at tens of kilometers per second, and yet still take years to reach Saturn. The paradox dissolves when the distance scale is kept in view. Saturn is roughly 1.5 billion kilometers from the Sun, and Earth is about 150 million kilometers from the Sun. Moving from Earth's orbit to Saturn's orbit is not adding a few hundred million kilometers of distance like crossing an ocean. It is adding more than 1 billion kilometers in orbital radius. The curved path includes much more than a simple radial increase. Speeds that are huge in human terms are not huge enough to compress such distances into months without extremely high energy. Another way to ground speed is to compare spacecraft speed with planetary orbital speed. Earth moves around the Sun at about 30 kilometers per second. Saturn moves at around 10 kilometers per second. A spacecraft that departs Earth has Earth 30 kilometers per second heliocentric speed as a starting point. To reach Saturn, it needs to change its energy so that its orbit extends outward. That does not always mean it must have a much higher speed than Earth. In a low-energy transfer, the spacecraft's heliocentric speed near Earth is slightly higher than Earth's, allowing it to climb outward, and then it slows to near Saturn's orbital speed at the far end. In a higher energy transfer, the spacecraft may depart with a much higher heliocentric speed, arriving sooner, but approaching Saturn with a higher relative speed. The key translation for human time is that the spacecraft's speed relative to the Sun is already in the same category as Earth's, yet the distance to Saturn is so large that the journey spans multiple Earth orbits. A spacecraft that takes 6 years to reach Saturn's distance will see Earth complete 6 revolutions around the Sun during the cruise. This is a simple way to visualize the timeline. The spacecraft is not out of the solar system during this time. It remains in a solar orbit. It is moving outward and around while Earth continues its annual cycle. Human time remains meaningful because the mission is experienced from Earth with seasonal cycles and yearly planning. Mission teams schedule operations over this multi-year span. The spacecraft's timeline is built in days and months, with key events such as trajectory, correction maneuvers, instrument checkouts, possible flybys and arrival sequences. Each of these is marked on calendars. The cruise phase may appear quiet, but it is managed. Navigation requires tracking the spacecraft's position and velocity through radio signals. Small corrections are made to keep the aim precise. Over billions of kilometers, small angular errors become large lateral offsets. A correction of a few meters per second early can prevent a miss by thousands of kilometers later. This reinforces the relationship between small speed changes and large changes in where and when the spacecraft arrives. Human time is filled with these scheduled corrections and checks, yet the underlying reason for the long duration is still the same: the speed profile and the distance scale. Another important speed-related element is the speed of the spacecraft relative to Earth, as it leaves the Earth-Moon system and enters interplanetary space. This relative speed affects how quickly the spacecraft leaves the region where Earth dominates, and how soon it becomes a deep space object. That transition is rapid. Within days or weeks, the spacecraft can be far enough that Earth appears as a point, and the Sun is the dominant reference. This means the feeling of departure happens early, but the majority of the travel time comes later in the long arc through the outer solar system. For human time, this can create a mismatch. The launch is dramatic and quick. The cruise is long and steady. The arrival is again intense and scheduled. This structure is common in deep space missions, and it is part of how the journey is lived through calendars and shifts. Saturn travel time in human units therefore includes a long middle span where the spacecraft is simply en route. If the route includes gravity assists, the speed discussion becomes more layered. A gravity assist can change the spacecraft's heliocentric speed without using fuel effectively increasing or decreasing its energy. A Jupiter gravity assist, for example, can be used to boost the spacecraft towards Saturn more efficiently. This can reduce the required launch energy, or in some designs, shorten the overall time if the assist allows a higher energy path than would otherwise be possible. Yet because gravity assists require visiting another planet first, they can also lengthen the path and the time. The speed gained is paid for with a detour and with waiting for the correct alignment. Thus, speed and time do not have a simple direct link. Higher speed at some phases does not guarantee shorter total time if the route includes additional legs. This reinforces the earlier lesson that time is a product of the whole trajectory, not just of the peak speed. Still, for a direct baseline like a Hohmann transfer, the speeds implied are consistent with a 6-year trip. The spacecraft's heliocentric speed near Earth is in the range of Earth's speed, and it slows as it approaches Saturn's distance. The path's period sets the time. The human meaning is that the spacecraft is moving quickly by everyday standards every second of the way, yet because the distance scale is so large and because the path is an orbital arc, the mission passes through multiple Earth years before arrival. This section therefore grounds the scale without introducing unnecessary numbers. The most useful conclusion is simple and stable. Interplanetary speeds are tens of kilometers per second. Those speeds correspond to hundreds of thousands to millions of kilometers per day. Saturn is more than 1 billion kilometers away in straight-line distance and requires a curved transfer between orbits. The result is a travel time measured in years for fuel-efficient routes. With this speed-to-time grounding in place, the next step is to look at real journeys that have been completed using past missions to Saturn as measured examples. Those missions show what reaching Saturn has taken in actual calendar years, and they reveal how choices like gravity assists and launch energy change the timeline within a realistic range. Real missions provide the clearest translation between the abstract language of orbits and the lived language of calendars because they place departure and arrival on dates that can be counted in years and months. Saturn has been reached by spacecraft on several different kinds of trajectories, and each trajectory reflects a different balance between available launch energy, desired arrival conditions, and the use of gravity assists. When these journeys are described in human time, the numbers stop being theoretical. They become spans that include multiple Earth seasons, multiple cycles of mission staffing, and long intervals where a spacecraft is simply in cruise. The earliest encounters with Saturn come from the era when deep space navigation and long-lived spacecraft are still being proven. A spacecraft can be launched from Earth and then guided outward for years with only small corrections relying on the Sun's gravity to carry it across the outer solar system. One early example is Pioneer 11. It launches in April of 1973 and reaches Jupiter first, using a flyby to reshape its path outward. It then arrives at Saturn for a flyby in September of 1979. In human time, this is about 6 years and several months from launch to Saturn encounter. The journey fits closely with the low energy expectation for reaching Saturn's distance, and it demonstrates that a multi-year cruise is achievable with the technology of the time. The Saturn encounter is not an orbital capture. It is a fast passage through Saturn's environment, yet it counts as reaching Saturn in the practical sense that the spacecraft enters Saturn's region, measures its fields and particles, and returns data to Earth across a light time delay that is already well beyond the immediate. The mission shows that years-long travel is not only a mathematical output of orbital mechanics, it is a workable operational timeline. A second set of examples comes from the Voyager missions, which are designed for grand tours of the outer planets and are launched in a period when planetary alignment allows sequences of flybys. Voyager 1 launches in September of 1977 and reaches Jupiter in March of 1979. It then reaches Saturn in November of 1980. In human time, the trip from launch to Saturn is a little more than 3 years. Voyager 2 launches in August of 1977, reaches Jupiter in July of 1979, and reaches Saturn in August of 1981. In human time, this is about 4 years from launch to Saturn. These times are shorter than the Hohmann-like baseline of around 6 years, because the Voyager trajectories are higher energy, and because they are optimized for fast passage and for specific flyby geometry, rather than for fuel minimal transfer and gentle arrival speeds. A faster trajectory reduces cruise duration, but it comes with a higher approach speed at Saturn, which suits flyby science and onward travel, but does not suit capture into orbit without a very large braking maneuver. The Voyager journeys therefore illustrate a clean trade. Saturn can be reached in closer to 3 to 4 years if the spacecraft accepts a faster path and a flyby encounter rather than orbit insertion. These missions also show how human time is structured during the cruise. The long intervals between planets are filled with navigation updates, instrument checkouts, and careful planning for the brief encounter windows which last days compared with the years of travel. The missions demonstrate that reaching Saturn is not a single continuous act of motion. It is years of coasting shaped by gravity and a short period of intense activity near arrival. The most detailed example of reaching Saturn in a sustained way comes with Cassini, a mission designed not only to pass Saturn, but to enter orbit and study the planet and its moons over many years. Cassini launches in October of 1997. It does not travel straight outward on a simple transfer. It uses a series of gravity assists to gain energy and to shape its approach so that the spacecraft can reach Saturn with a trajectory suitable for orbital insertion. The route includes flybys of Venus, a return flyby of Earth, and a flyby of Jupiter, each timed to provide a change in heliocentric velocity without requiring enormous propellant expenditure. These assists add complexity and add path length, but they also reduce the required launch energy and enable the spacecraft to arrive with conditions that support the planned capture. Cassini arrives at Saturn in July of 2004, when it performs a major burn to enter orbit. In human time, the journey from launch to orbit insertion is about 6 years and 9 months. This duration sits slightly longer than the basic 6-year low-energy expectation, which is consistent with a path that includes inner solar system loops and a Jupiter flyby. The difference is not waste. It is a chosen way to make the mission possible with the available launch capability and spacecraft design, while still meeting the arrival needs of an orbital mission. Cassini also carries the Huygens probe, which separates and later descends through the atmosphere of Titan. Huygens reaches Titan and lands in January of 2005, about 6 months after Saturn orbit insertion. This provides a second kind of arrival marker. Reaching Saturn can mean arriving at the Saturn system and entering orbit, and it can also mean arriving at a specific moon with an atmospheric descent. Both are measured in the same calendar framework and both depend on the timing established by the interplanetary crews. Together, these missions define a realistic range for Saturn travel in human time using known propulsion. Flyby missions with higher energy paths can reach Saturn in roughly 3 to 4 years. More fuel-efficient or gravity-assist heavy paths tend to reach Saturn in roughly 6 to 7 years. The exact number depends on launch date, trajectory class, and the required arrival conditions. The evidence is not hypothetical. It is written into the dates and cruise durations of completed missions. This range also clarifies what is meant by measuring the journey in human time rather than in kilometers. A difference of 2 or 3 years is not a small adjustment. It changes the staffing of the mission team, the timing of instrument aging, the planning for software updates, and the endurance required of power systems. It also changes how many Earth seasons pass between launch and arrival. In the 3-year case, the mission team plans across a span that is long but compact, with many members remaining in their roles from launch through arrival. In the 7-year case, roles and systems can change more, and the spacecraft must be designed for longer cruise reliability. Human time also includes the slow drift of communication delay as the spacecraft moves outward. During the early months after launch, communication delays are still short. Commands and data return are separated by minutes. As the spacecraft reaches the outer solar system, the delay stretches toward an hour and beyond, changing how quickly problems can be diagnosed and how far ahead sequences must be planned. These operational rhythms become part of the lived time of the journey. A Saturn mission becomes less like driving toward a destination and more like sending a carefully prepared schedule forward in time, with confirmation arriving long after the fact. Another point that real missions make clear is that the phrase "reach Saturn" can mean different physical events. For a flyby, reaching Saturn is the moment of closest approach, when the spacecraft passes through the region where Saturn's gravity and environment dominate the local dynamics and measurements. For an orbiter, reaching Saturn is the moment of orbit insertion, when the spacecraft performs a burn that changes its trajectory from an unbound path to a bound Saturn-centered orbit. The difference matters because it changes energy requirements and it shapes travel time. A flyby can accept a faster, shorter journey because it does not need to shed as much relative speed at arrival. An orbiter must plan for capture, which often favours trajectories that arrive with manageable approach speeds or that include planned braking. Cassini shows that an orbital mission can still reach Saturn within a human-scale span of years, but it also shows that achieving orbit requires additional planning and often a longer cruise than a simple fast flyby. In the calm measurement of human time, these missions provide a stable answer framework. Saturn is not reached in weeks or months by current chemical propulsion and realistic mission profiles. It is reached in years. The lower end of practical experience is around 3 years for a high-energy flyby path. The more common and flexible region is around 6 to 7 years for efficient transfers and for complex trajectories that trade time for energy management. This is the measured range that real journeys demonstrate. The next step is to translate this range into the human experience of the cruise itself, not as emotion but as calendar structure. How years in transit are partitioned, how the journey is paced by checkouts and corrections, and how the long cruise becomes a sequence of manageable time blocks before arrival. Once real missions place Saturn travel in a stable range of a few years to around 7 years, the outer region becomes the way that span is actually lived and managed in human calendars, because measured in human time is not only the final number of years, but the structure inside those years. A Saturn cruise is not a single uniform stretch of waiting. It is divided into phases that correspond to changing distance, changing communication delay, changing power conditions and planned navigation milestones. Each phase is counted in days and months nested inside the larger count of years. This nested structure is what makes a multi-year journey manageable for human institutions and for the people who operate the spacecraft. The first phase is departure, which takes minutes for launch, and then days to settle into the planned heliocentric trajectory. Launch day is dense with events and time-critical sequences. The spacecraft must reach Earth orbit or a departure trajectory, deploy antennas and solar arrays. If present, stabilize its attitude and establish a reliable radio link. The human time here is measured in minutes and hours. The next few days often include an early trajectory correction maneuver, a small engine burn to remove launch dispersions, and to place the spacecraft precisely on its intended path. This early correction is efficient because small changes early prevent large errors later. In human time, this phase still feels close to Earth because the spacecraft is still near enough that communication delays are short and the signal strength is high. The second phase is early cruise, which can last months. During this time, the spacecraft is steadily moving away from the Sun and from Earth, but it is still within the inner part of the solar system. If the trajectory includes inner-planet flybys, as in the case of gravity assist routes, this phase can include a pass near Venus or Earth. If it is a more direct route, it can be a clean outward arc. In either case, the spacecraft's systems are checked, instruments may be calibrated, and navigation tracking is frequent. Human time is measured in weeks of planning and in monthly activity cycles. The mission team develops a routine. There are scheduled communication passes, data, downlinks, and command uplinks. The spacecraft's path is refined through radio tracking, which measures Doppler shift and signal timing to estimate velocity and distance. These measurements are processed on Earth, and small trajectory corrections are planned when needed. The corrections themselves are short burns, but the planning and verification can take days or weeks, because the team must design sequences, test them, upload them, wait for them to execute, and then confirm outcomes after the relevant light time delay. During early cruise, the delay is still small enough that this loop is measured in hours rather than days. As the spacecraft moves farther, the delay grows and planning must be more anticipatory. The third phase is mid-cruise, which often spans years for a Saturn mission. This is the longest phase and the one that defines the calendar experience. A mission that takes 6 to 7 years to reach Saturn will spend most of that time in mid-cruise. In this phase, the spacecraft is far enough that the Sun appears smaller and weaker. Thermal conditions become more stable in some respects because sunlight variations are smaller, but the cold of deep space becomes more dominant. Power management becomes an ongoing concern. If the spacecraft uses solar panels, the reduced sunlight far from the Sun requires careful budgeting. If it uses a radioisotope power source, the power output declines slowly over time because of radioactive decay and hardware aging. The decline is predictable and is accounted for in planning. In either case, years of cruise require that systems remain within safe temperature ranges, and that electronics endure radiation exposure and component aging. Human time is used to schedule long-term checkouts and software updates. A spacecraft may be placed in a low-activity mode for long periods, with instruments off heaters controlled automatically, and attitude maintained with minimal fuel use. Periodically, the spacecraft is woken for checkouts. These checkouts are scheduled months in advance. They are built into a yearly operational calendar that repeats like a quiet season. The mission becomes a pattern of planned awakenings and long coasts, and the years are counted not only by dates but by these milestones. Navigation continues throughout mid-cruise, but the frequency of corrections may decrease once the trajectory is well established. Small correction burns are still used to trim the aim point and to adjust arrival conditions. The timing of corrections can be chosen to maximize efficiency and to support the later arrival geometry. As the spacecraft moves outward, the light time between Earth and the spacecraft increases. The delay changes the rhythm of decision-making. A command sent today is received later. A report of a spacecraft state change arrives later still. This means that the mission team cannot respond instantly to unexpected events. Instead, the spacecraft is designed for autonomy in basic safing behavior. If a fault is detected, the spacecraft can enter a safe mode, point its antenna toward Earth, and wait for instructions. The team then receives telemetry after the light time delay and plans recovery sequences. In human time, a fault can take days to resolve, not because the repair is complex, but because the conversation with the spacecraft is slow. This is one of the clearest ways Saturn distance is felt as time. The fourth phase, if the mission uses gravity, assists includes encounter phases with other planets. These encounters are intense and time-critical, like a small preview of the arrival. During a flyby, the spacecraft must hit a narrow corridor in space at a precise time, because a flyby is both a scientific opportunity and a navigation event. A small error in timing or position can change the resulting trajectory significantly. The mission team therefore increases tracking and planning in the months leading up to the flyby. Commands and observation sequences are prepared carefully. The flyby itself may last only hours at closest approach, but its effects on the spacecraft's path and on the mission timeline last years. In human time, these encounters become anchor points that divide the long cruise into chapters without requiring chapter titles. After each flyby, there is a period of assessment and trajectory update, and then the mission returns to a quieter cruise routine. The fifth phase is approach, which begins months before arrival at Saturn. Approach is when the destination's presence becomes measurable in navigation terms and in science planning. The spacecraft's trajectory is refined to target a specific arrival geometry. If the mission is a flyby, the aim point is set for closest approach and for desired ring plane crossings and moon encounters. If the mission is an orbiter, the aim point is set for the orbit insertion burn, which must occur at a precise time relative to Saturn. Approach planning is intense because the arrival event is often unrepeatable. If an orbit insertion burn fails, the spacecraft may fly past Saturn and be lost to the mission's main goals. Therefore, the final months include frequent tracking rehearsals of sequences and careful verification of propulsion system readiness. Human time in approach is measured in weeks and days with key review dates and timeline milestones. Communication delay by then is long, so sequences are often uploaded well ahead of time, and the spacecraft executes them autonomously. The team waits for confirmation, knowing that by the time a problem is detected on Earth, the moment for intervention may have passed. This operational reality is not presented as drama. It is a natural consequence of distance and light time. The arrival itself occupies a small fraction of the total travel time. Closest approach in a flyby might be minutes of peak data collection, inside days of encounter operations. Orbit insertion might be a burn lasting tens of minutes inside weeks of approach operations. Yet those minutes are the payoff of years. This is how Saturn travel is structured in human time. The years are not empty. They are a long scaffolding of routine operations designed to preserve the spacecraft and to deliver it to a precise place at a precise time. In this framing, how long it would take is a measured number of years, but it is also the sum of many smaller time commitments and constraints: launch windows, checkouts, navigation cycles, light time delays, and arrival rehearsals. A 6-year cruise includes thousands of days, and each day is accounted for in planning documents and tracking logs. The spacecraft does not experience boredom, it follows physics. The human teams experience the passage of time through schedules, staffing changes, and the slow approach of a date that is placed on the calendar years ahead. The translation from orbital mechanics to human time therefore ends up being a translation from continuous motion to discrete planning units. The next step is to quantify the communication delay more precisely as a separate form of Saturn distance in time, because even when the travel time is years, the signal delay is a daily operational limit that is always present, and that changes predictably with the Earth-Saturn geometry. Communication delay is the simplest and most direct way to express Saturn's distance in human time, because it converts kilometers into minutes without any dependence on spacecraft, propulsion, mission design, or engineering choice. The delay is set by one constant, the speed of light. Radio signals travel at the speed of light through space, and that speed is fixed. This means that for any moment in time, if the distance between Earth and Saturn is known, the one-way signal time is simply that distance divided by the speed of light. The result is the light time, and it is a daily operational reality for spacecraft near Saturn. Unlike travel time, which depends on the chosen trajectory and can vary from about 3 to 7 years for past missions, light time depends only on orbital geometry and changes smoothly as Earth and Saturn move around the Sun. This section keeps the focus on that changing geometry and on the practical meaning of the delay. The scale begins with the astronomical unit. One astronomical unit is about 150 million kilometers and corresponds to about 8 minutes of light travel time. Saturn's distance from the Sun is about 9.5 astronomical units. Earth's is 1. The distance between Earth and Saturn therefore ranges roughly between about 8.5 astronomical units and about 10.5 astronomical units, depending on whether Saturn is near opposition or conjunction. Multiplying those separations by 8 minutes gives a one-way light time range from roughly a little over 1 hour to roughly 1 hour and 20 minutes or more. In more concrete terms, 1 hour is 60 minutes. 8.5 astronomical units corresponds to about 68 minutes. 10.5 astronomical units corresponds to about 84 minutes. These values are approximate because the astronomical unit is not exactly 8 minutes of light time, and because the orbits are not perfect circles, but they are close enough to define the human scale. When a spacecraft is operating at Saturn, a command sent from Earth takes on the order of 1 hour to reach the spacecraft. The spacecraft's response takes on the order of another hour to return. This is the round-trip light time. It can therefore range from roughly a bit over 2 hours to nearly 3 hours depending on geometry. This is the minimum possible feedback loop. Even if the spacecraft's computer responds instantly, the round-trip time cannot be reduced. This is not a technical delay. It is a distance delay. The operational consequences are straightforward. Spacecraft at Saturn cannot be piloted in the sense of steering continuously from Earth. There is no joystick. There is no immediate correction to a developing situation. Instead, operations are planned as sequences that the spacecraft will execute on its own. The spacecraft is given a timeline of commands and conditional logic. It carries out the plan store's data and then transmits the data back when scheduled. If something unexpected happens, the spacecraft relies on its onboard fault protection. It can detect conditions that exceed limits and can enter a safe configuration. It can point its high-gain antenna toward Earth and wait. The mission team then receives the telemetry after the one-way delay diagnoses. The situation prepares a recovery sequence, sends it, and waits again for confirmation. A problem that might take minutes to diagnose in a nearby system can take many hours or days at Saturn because each exchange costs multiple hours. This is why the communication delay is often described as the closest thing to a distance wall in mission operations. It is always present, and it cannot be engineered away. The delay is also not constant day to day. Earth and Saturn continue to orbit the Sun during the mission. When Earth is moving toward opposition relative to Saturn, the one-way delay decreases slowly. When Earth is moving toward conjunction relative to Saturn, the one-way delay increases slowly. The rate of change is not fast. Over days the change is small. Over months it is noticeable. Mission teams track this and plan accordingly. The changing delay also affects data return rates indirectly. Radio signal strength decreases with distance, so when Saturn is farther from Earth, the signal is weaker, all else equal, and the data rate may be reduced, or the spacecraft may need to use longer downlink sessions. Atmospheric and antenna constraints on Earth also matter, but distance sets the baseline. Thus, as Earth and Saturn move, the time delay and the ease of communication drift in a predictable cycle. This cycle is a quiet clock that runs alongside the mission's larger calendar. Communication delay also interacts with the Sun. When Saturn is near conjunction, the line of sight from Earth to Saturn passes close to the Sun. The solar corona, the outer atmosphere of the Sun, is filled with plasma that can disturb radio signals. Signals passing close to the Sun can be scattered and delayed slightly, and can suffer increased noise. During solar conjunction, missions often reduce communication, or avoid critical operations because the link becomes less reliable. The delay itself in terms of light time is largely geometric, but the quality of communication can be degraded. In human time, conjunction can create a period of days or weeks, when operations are intentionally quiet with the spacecraft executing minimal activities, while the Earth link is compromised. This is another way the solar system's moving geometry shapes a Saturn mission's timeline. Saturn travel time is measured in years, but during those years there are intervals where communication is routine, and intervals where communication is restricted by solar geometry. The light time delay can also be used as a mental measure of distance that is more natural than kilometers. A distance of 1.5 billion kilometers may be hard to picture. A delay of 70 to 80 minutes is easier to integrate into daily experience. It is longer than a lunch break and shorter than a long meeting. It is long enough that a person can send a message and do other work before any reply could possibly arrive. This human-scale framing is useful because it makes the remoteness of Saturn immediate. The spacecraft is not in a place where Earth can reach out quickly. Every action is separated from Earth by more than an hour of time. The mission is therefore inherently delayed. It becomes a practice of anticipation and verification rather than of immediate control. Communication delay also defines the pace of emergencies. If the spacecraft enters safe mode unexpectedly, the earliest moment the mission team can even learn about it is after the one-way delay plus the time needed for the spacecraft to transmit the relevant telemetry. In some cases, the spacecraft may stop sending high-rate data and send only a carrier signal or a minimal beacon that indicates a safe mode state. The team then schedules deeper communication sessions to retrieve more detail. Each step is paced by the delay. Even under ideal conditions, the response cycle is hours. Under constrained communication, it can stretch longer. This is why deep space spacecraft are designed with robust autonomy and with conservative safing rules. They must protect themselves for hours or days without immediate human guidance. This is a practical implication of the speed of light. Another aspect of communication is navigation. Deep space navigation relies on radio tracking, including Doppler measurements and range measurements. The time delay affects how quickly tracking data can be received and processed. But the more important issue is that navigation solutions are built from long arcs of data collected over hours and days. A spacecraft at Saturn is tracked regularly, and its orbit and trajectory are estimated with high precision. Small maneuvers can be planned to adjust its path. The delay does not prevent navigation. It simply adds latency to the loop. This latency is manageable because spacecraft dynamics change slowly compared with the delay. In the Saturn system, orbital periods of moons are measured in days, and spacecraft orbital periods can be days to months. In that context, a 2-hour round-trip delay is significant, but not crippling if operations are planned. It becomes a constant background condition. The delay also has a psychological aspect for humans on the ground, but in this script it remains a practical fact. It shapes planning, it shapes autonomy requirements, and it shapes the division of work into sequences. Communication delay thus provides a clear and stable answer in human time alongside the travel duration. Reaching Saturn takes years of cruise, but communicating across the Earth-Saturn gap takes more than an hour one way. Both are measures of distance expressed as time. One describes motion, the other describes connection. Together they define what Saturn means in human time, a destination that requires long planning and patient operations, and a system where every exchange with a spacecraft is stretched across hours. With this concept established, the next step is to examine the ways travel time can be reduced or modified, not by wishing for speed, but by selecting higher energy trajectories and by using gravity assists. These options will be described as trade-offs in time fuel and arrival conditions, keeping the focus on what is possible with known physics and demonstrated mission design. Once communication delay makes Saturn's remoteness immediate in minutes and hours, the outer region returns to the years of travel and asks how that travel time can be changed by trajectory choice. The key point is that there is no single travel time to Saturn, even within known physics. The cruise duration is a variable that can be traded against fuel launch energy, spacecraft mass, and the desired arrival conditions. Faster travel is possible, but it is not free. It requires higher energy, and higher energy typically means a larger delta V requirement, or a more powerful launch vehicle, or it requires a carefully arranged sequence of gravity assists. Each option has a cost. The calm way to describe these options is to treat time as one side of a balance. A lower energy route minimizes fuel and often uses a Hohmann-like transfer time of roughly 6 years. A higher energy route shortens the flight by placing the spacecraft on a more energetic heliocentric trajectory, whose period is shorter for the outward leg. In the simplest sense, the spacecraft departs Earth with a larger hyperbolic excess speed, meaning it leaves Earth not just escaping, but doing so with a substantial extra speed relative to Earth. In the Sun's frame, this translates into a higher heliocentric energy. The spacecraft's orbit becomes less tightly bound with a smaller time to reach Saturn's distance. The result can be a flight time closer to 4 years, or in some cases closer to 3 years, as demonstrated by the Voyager missions. This is the high-energy direct approach. It is a straightforward way to shorten time, but it imposes several consequences. The first is the requirement at launch. Providing a high departure energy demands either a powerful rocket or a lighter spacecraft or both. Launch vehicles have limits. Increasing departure energy can reduce the mass that can be sent, which can limit instruments shielding fuel reserves and redundancy. It can also raise mission cost and complexity. The second consequence is arrival speed. A faster heliocentric trajectory typically reaches Saturn, with a higher velocity relative to Saturn. For a flyby mission, this is acceptable and can even be useful because a fast flyby allows the spacecraft to continue onward to other destinations or out of the solar system. For an orbiter, a high relative speed is a problem because capture requires removing that speed. The required braking maneuver at Saturn would be large, consuming propellant and increasing spacecraft mass. If the spacecraft cannot carry enough propellant, a fast direct route can make orbit insertion impossible. Therefore, higher energy transfers tend to favor flybys or require other ways to manage arrival energy. One way to manage arrival energy is to accept a long looping approach that arrives with a lower relative speed. Another is to use gravity assists to shape the trajectory in a way that reduces the net propellant requirement. Gravity assists are often described as free boosts, but they are better described as exchanges of momentum with a moving planet that can change the spacecraft's heliocentric velocity vector. Gravity assists can increase the spacecraft's energy, decrease it, or rotate its direction. A gravity assist can therefore be used both to speed up a mission and to slow down or reshape the approach for capture. The trade is that gravity assists impose geometry constraints. The spacecraft must arrive at the assisting planet at the right time and with the right approach angle. This can add travel time because the spacecraft may need to loop inward or sideways rather than moving steadily outward. The Cassini mission shows this trade clearly. Cassini uses multiple inner planet flybys and a Jupiter flyby. This sequence allows it to reach Saturn with the needed arrival conditions for orbit insertion without requiring an impossibly powerful launch. The cost is a cruise time of nearly 7 years longer than a simple fast direct flyby could be. Thus, gravity assist can reduce required launch energy and enable orbit insertion, but they can lengthen the calendar time to arrival. Still, gravity assist can also shorten travel time in some cases. A Jupiter gravity assist, for example, can provide a significant change in heliocentric velocity that can help a spacecraft reach Saturn more quickly than a low-energy direct transfer would, depending on the mission's design and constraints. The key is that Jupiter is itself far from Earth at about 5 astronomical units. Reaching Jupiter already takes time and the sequence must line up. Whether the total time is shorter depends on whether the assist replaces a longer low-energy arc with a shorter multi-leg path. This is a design choice. Another way travel time can be modified is by using different classes of transfer that are not strictly Hohmann. A bielliptic transfer, for example, uses 2 elliptical legs with an intermediate aphelion farther than the destination orbit. For some orbit changes, a bielliptic transfer can reduce delta V at the cost of significantly more time. For reaching Saturn, such a transfer is generally not used as a primary method because it would lengthen time greatly, but it illustrates the general rule: time can be traded for fuel by choosing trajectories with longer periods and more distant aphelia. At the other extreme, a powered trajectory with continuous low thrust, such as ion propulsion, can gradually increase heliocentric energy over long periods. Ion propulsion provides small thrust but can operate for months or years, achieving high total delta V, with less propellant mass than chemical rockets. However, the thrust is weak, so the acceleration is tiny, and the overall travel time is not necessarily shorter unless the mission is designed specifically for it and has sufficient power. Ion propulsion can be excellent for reshaping orbits and for certain deep space missions, but reaching Saturn quickly still faces the constraint that high power is needed to run high-thrust electric propulsion, and power is harder to obtain far from the Sun. Nuclear power can supply electricity, but that introduces other design constraints. In human time, terms electric propulsion often supports flexible trajectory shaping, but does not automatically mean faster arrival. It can mean a different distribution of time and thrust with a long thrusting phase, instead of short burns. Another factor is the destination definition. If reach Saturn means a flyby, time can be shortened because no capture is required. If it means orbit insertion, the time might be longer, because the trajectory must support a manageable approach speed and a planned insertion burn. If it means reaching a specific moon on a specific geometry, time can change again because the spacecraft may need additional time after Saturn arrival to adjust its orbit using moon flybys. A mission can reach the Saturn system in 6 to 7 years, but then take additional months or years to reach a particular orbit around a moon. In human time, this means that reaching Saturn can be the start of a new phase rather than the end. Still, the focus here remains on the interplanetary cruise to the Saturn system itself. In that context, the practical range demonstrated so far is a few years for fast flybys and around 6 to 7 years for transfers that balance energy needs and support orbital missions. Shortening below 3 years would demand extremely high departure energy or novel propulsion not yet demonstrated for such missions. Even within the 3 to 4 year range, the cost in launch energy and arrival speed is significant. Therefore, the calm conclusion of this region is that Saturn travel time is adjustable but bounded. Time can be reduced by increasing energy, but energy costs rise quickly and create arrival complications. Time can be increased to save energy by using gravity assists and longer period arcs. Gravity assists can enable missions that would otherwise be impossible and can tailor arrival conditions, but they impose timing constraints and can lengthen the calendar time. These are the practical trade-offs of reaching Saturn with known physics. The next step is to state the underlying physical limits more plainly, not as an absolute barrier to exploration, but as a set of constraints that define why Saturn travel sits in the range it does, and why for human missions in particular, human time becomes not only years but questions of endurance shielding and life support across those years. The range of Saturn travel times seen in theory and in practice is not arbitrary. It is shaped by a set of physical limits that are already present in the earlier sections. The way orbits set timescales, the way propulsion sets achievable energy, and the way space itself imposes hazards that grow with speed and duration. The outer region here is the limit set by known propulsion, and by the energy required to shorten, time described calmly as constraints rather than as dramatic barriers. The first limit is orbital timescale. A low-energy transfer is an orbit around the Sun, and the time to move from Earth's distance to Saturn's distance is tied to the period of that orbit. For a transfer ellipse that reaches Saturn's orbit, the time naturally falls in the range of several years. This is a consequence of the size of the solar system and the Sun's gravity. To make the time much shorter, the spacecraft must be placed on a more energetic trajectory, closer to a hyperbolic escape path where it spends less time rising outward. That is possible, but it requires much larger departure energy. This leads to the second limit: propulsion energy and mass. Chemical rockets provide high thrust for short durations. They can deliver large velocity changes at launch, but they do so by consuming propellant rapidly. The amount of propellant required grows quickly as the required delta V increases. Because a spacecraft must carry its propellant and propellant adds mass, there is a steep trade between how much delta V can be achieved and how heavy the spacecraft can remain. For missions beyond Earth orbit, the launch vehicle must provide the initial energy. If more energy is demanded, either a more powerful rocket is needed, or the spacecraft must be lighter, with fewer instruments, less shielding, less redundancy, and less propellant for later maneuvers. This is why very fast direct transfers are rare, and why the 3 to 4 year range is associated mainly with flybys and with trajectories that accept high arrival speeds. The third limit is arrival speed management. A spacecraft arriving quickly at Saturn tends to arrive with a high velocity relative to Saturn, because its heliocentric trajectory is more energetic. If the goal is to fly past, the spacecraft can accept this and simply pass through the Saturn system. If the goal is to orbit Saturn, the spacecraft must remove enough relative speed to be captured. Removing speed requires either a large engine burn near Saturn or some other mechanism to shed energy. Aerobraking, which uses an atmosphere to slow a spacecraft, is difficult at Saturn because there is no solid surface, and because controlling a spacecraft through deep atmospheric passes at high speed in a giant planet's atmosphere is complex and risky. Some missions use atmospheric drag at Mars and Venus, but the Saturn environment is different and has not been used in the same routine way for major capture. Therefore, orbit insertion generally requires propellant. The requirement to carry propellant for insertion pushes the spacecraft mass upward, which then pushes the needed launch energy upward, which then makes fast transfers harder. This is a coupled constraint. It is one reason that an orbiter like Cassini follows a longer trajectory with gravity, assists arriving with conditions that make orbit insertion feasible with the available propellant and launch capability. The fourth limit is the hazard of interplanetary and interstellar dust at high speed. Space is thin, but it is not empty. It contains dust grains and small particles. At ordinary spacecraft speeds of tens of kilometers per second, these particles can still cause damage, but the risk is manageable with shielding and careful design. If speeds were pushed much higher to shorten travel time drastically, each dust impact would carry much higher kinetic energy, because kinetic energy increases with the square of speed. A small grain that is harmless at low speed can become damaging at high speed. For a journey of billions of kilometers, the spacecraft will encounter many particles over time. Thus, increasing speed is not only a propulsion problem, it is also a survivability problem. It increases the stress on shielding and on vulnerable components. This is a physical constraint that becomes more severe as one attempts to compress time by raising velocity. The fifth limit is the endurance of systems over long durations. While the previous limits act to prevent travel from becoming too fast, endurance acts to prevent travel from becoming too long without added cost. A spacecraft on a 7-year cruise must maintain power thermal control and communication for 7 years before arrival, and then often for many years after arrival if it is an orbiter. Hardware ages. Radiation can damage electronics and degrade solar cells. Mechanical components such as reaction wheels can wear. Propellant for attitude control is finite. Software must remain robust and sometimes must be updated. These are engineering constraints rather than fundamental physics limits, but they are grounded in physical wear and in the environment. They set practical upper bounds on how long a mission can cruise before arrival without increasing cost and complexity. This is why mission designers often aim for travel times that are long enough to be energy efficient, but not so long that endurance becomes the dominant risk. In the Saturn case, the natural low energy time of around 6 years sits in a region that is challenging but manageable. Longer routes can be used, but each extra year increases risk and operational cost. The sixth limit becomes relevant when considering human travel rather than robotic travel. The question prompt describes Saturn travel in human time, which can mean time as humans count it, but it can also naturally raise the idea of human presence. If humans were to travel to Saturn with current or near-term propulsion, the travel time would still be years, and the constraints would expand. A multi-year human mission would require life support that can operate reliably for years without resupply protection against radiation, protection against the psychological and physiological effects of long-duration confinement, and a way to manage emergencies without quick return. It would also require substantial mass because habitats shielding food, water, and redundancy add weight. More mass means more energy required to accelerate and decelerate. This would make fast transfers even harder. Thus, the human scale is not only the calendar, it is the mass and support needs of human life. In the context of known physics, this reinforces the idea that reaching Saturn quickly is difficult, and that reaching Saturn at all with humans would be a major extension beyond current mission profiles. The script remains cautious and does not claim what will or will not be built. It states the constraint human requirements increase mass and complexity, and that shifts the trade-offs toward longer lower energy trajectories unless new propulsion methods are developed. The seventh limit is the finite speed of information. Even if a spacecraft could reach Saturn faster, the communication delay would remain more than an hour one way because the distance is set by orbital geometry. For human missions, this means that Saturn is outside the range where near real-time assistance from Earth is possible. Crew autonomy would be essential. This is not an added difficulty. It is built into the speed of light. It means that the Saturn system is operationally a deep space environment in the strongest sense. The combined effect of these limits explains why Saturn travel time in the real history of spaceflight clusters where it does. A low-energy direct transfer yields about 6 years. Gravity assist routes can yield similar or somewhat longer times, while reducing launch energy needs and enabling orbit insertion. Higher energy routes can reduce travel time to around 3 to 4 years, but they generally favour flybys and require higher departure energy and accept higher arrival speeds. There is no simple way to reduce the travel time to months with current propulsion while keeping payloads and arrival conditions reasonable. The constraints are energetic, mechanical, and environmental. In human time, this means Saturn is a destination that requires planning across years, not across seasons. It also means that the timescale is still within the scope of long, scientific missions and within the human capacity to manage long projects. The journey is not beyond comprehension, it is beyond quickness. This section therefore completes the calm statement of limits. It does not suggest that exploration stops at Saturn. It clarifies why Saturn travel time has the values it has, and why those values persist across different mission designs. The next step is to return to the moving nature of the destination, describing how Saturn's motion and the changing geometry of arrival shape the final months and days of a mission, and how the destination does not wait in place, making timing itself a fundamental part of reaching Saturn in human time. Saturn's motion is a quiet but decisive part of the timeline because the destination is not a fixed point that can be approached whenever a traveller arrives. Saturn continues to orbit the Sun throughout the mission, and the spacecraft must meet it at a particular place and time. This makes reaching Saturn an exercise in synchronizing clocks, the spacecraft's transfer time, and Saturn's orbital position. In human time, this synchronization is why launch windows exist, why arrival dates are chosen years in advance, and why the final months of approach are focused on timing and aim point refinement. Saturn's orbital period is close to 30 Earth years. This means Saturn moves slowly across the background stars in the sky from Earth's perspective, but it does not mean Saturn is nearly stationary. Saturn still travels through space at about 10 kilometers per second around the Sun. Over one Earth year, Saturn moves through a noticeable fraction of its orbit. Over the several years of a mission cruise, Saturn moves a large distance along its path. For a 6-year transfer, Saturn advances by roughly 1/5 of its orbit. The spacecraft must arrive at the point in space where Saturn will be not where it was. This requirement is built into trajectory design from the start. A planned transfer orbit is computed to intersect Saturn's orbital path at a specific time. The launch date is chosen so that Earth's position at departure lines up with Saturn's position at arrival through the geometry of the chosen trajectory. This is why a mission cannot launch any day and still reach Saturn on the same path. If the spacecraft departs too early or too late, the intersection will occur when Saturn is elsewhere and the spacecraft will miss. To correct such a mismatch would require significant changes in velocity, which would demand propellant beyond what is normally available. Therefore, timing is a resource as real as fuel. It is conserved by planning. In practice, the mission is designed with a specific arrival date window. Within that window, trajectory corrections can trim the aim point, but the overall schedule is set by orbital geometry. Human time is therefore embedded in celestial time from the beginning. The concept of a launch window can be described plainly. For any chosen transfer time, there is a required angular separation between Earth and Saturn at departure. This separation is called the phase angle. It is the amount Saturn must be ahead or behind relative to Earth in their orbits at the moment of departure, so that after the spacecraft travels for the chosen time, it arrives at Saturn's position. If the spacecraft's travel time is shorter, Saturn moves less during the cruise, and the required phase angle is different. If the travel time is longer, Saturn moves more, and the required phase angle changes. Because Earth moves faster than Saturn, the phase angle condition recurs periodically. Earth catches up to Saturn in relative alignment on a cadence of about 1 year. This does not mean there is a perfect window every year for every possible trajectory, because the details depend on other constraints, but it means the timing opportunities are frequent enough that missions can be scheduled within a decade-scale planning horizon. In human time, this is why Saturn missions are feasible. The solar system provides recurring alignments. Still, the window can be narrow. A direct high-energy trajectory might have a launch period of weeks. A gravity-assist trajectory might have a window defined not only by Saturn, but by the alignment of Venus, Earth, and Jupiter as well. This can narrow options further. Missing the window can delay the mission by months or years because the geometry must repeat. The practical consequence is that launch schedules are built around celestial mechanics, and the project timeline includes deadlines that are not negotiable once the launch date is chosen. Saturn's motion also shapes arrival geometry. An arrival at Saturn is not only a meeting in space, it is a meeting with a moving planet in a moving system. The spacecraft's approach, direction, and speed relative to Saturn depend on how the heliocentric trajectory intersects Saturn's orbit. If the mission is an orbiter, it may prefer an approach that allows the orbit insertion burn to produce a useful initial orbit around Saturn, often a highly elliptical orbit that can later be adjusted. The approach may be designed to pass through a particular region of Saturn's system, perhaps near the plane of the rings, or near a particular moon's orbit to set up later encounters. If the mission is a flyby, the approach may be designed for a close pass of a specific moon, or to pass through particular magnetospheric regions. These choices are tied to arrival timing because the moons orbit Saturn with their own periods. The arrival date sets which moons are where, and the approach path sets which encounters are possible. For Cassini, arrival at Saturn is followed by an orbital tour that uses repeated flybys of Titan and other moons to reshape the orbit. The geometry of these flybys depends on when the spacecraft arrives and on how it is captured. In human time, this means that reaching Saturn is not a single endpoint, but an entry into a timed choreography. The initial arrival sets the rhythm for months and years of subsequent operations. Even for a simple flyby mission, the timing affects what can be observed. Saturn's rings are tilted relative to its orbit plane, and the ring's apparent tilt as seen from Earth changes over Saturn's long year. There are periods when the rings are open, and periods when they are edge-on. A spacecraft approaching Saturn sees the ring system from a particular angle, determined by the season in Saturn's orbit, and by the approach trajectory. This affects what features are visible, and how measurements are planned. For example, certain ring plane crossings may be easier at certain geometries, and certain shadowed regions may be present depending on sun angle. These are scientific concerns, but they tie back to timing. The destination's appearance and the optimal measurement plan depend on when arrival occurs. This is another way Saturn does not wait. It changes with time. Approach navigation in the final months is a practical response to this moving target. Navigation teams use radio tracking to refine the spacecraft's trajectory and to predict the time and location of closest approach or orbit insertion. Small correction burns are planned to adjust the arrival time by minutes or hours, and to adjust the aim point by hundreds or thousands of kilometers. These adjustments sound small compared with a billion-kilometer scale, but they are crucial because the encounter corridor near Saturn can be narrow. For a flyby, missing the intended aim point can mean missing a planned moon flyby or passing through an unintended region of the rings. For an orbiter, missing the aim point can place the spacecraft too high or too low relative to the planned insertion geometry, potentially requiring more propellant to correct or risking safety. The final corrections are therefore scheduled carefully. Because communication delay is long, these burns are often executed autonomously, based on preloaded sequences. The team receives confirmation after the fact. In human time, the final weeks include rehearsals and verification, precisely because there is no last-second correction from Earth. The spacecraft must carry out the plan at the right moment. Saturn's motion also affects how arrival time is reported. A mission's arrival date is often stated in Earth calendar terms, but the spacecraft's encounter time is also related to Saturn's local time and to the geometry of the Sun-Saturn spacecraft alignment. The spacecraft may cross Saturn's ring plane at a certain Saturn local time, or pass behind Saturn, relative to Earth, causing a radio occultation. These events depend on the exact timing. In human time, they appear as schedule blocks ring plane crossing, at a certain hour closest approach, at a certain minute signal loss during occultation signal return. The background reason is the moving nature of the system. Earth and Saturn both move and the spacecraft is meeting them in motion. The quiet conclusion of this region is that reaching Saturn is fundamentally a timing problem as much as a distance problem. Distance sets the years. Timing sets which years and which days. The destination's motion sets the existence of windows, the need for phase angle alignment, and the precision of final approach corrections. The spacecraft arrives not in a static scene, but in a system where the planet, its moons, its rings, and its magnetic environment all change with time. Measuring travel in human time therefore includes not only how many years pass, but how those years are anchored to specific dates when the geometry is right. The next step is to gather the threads into a final measured view of Saturn travel within a human lifespan, and a human calendar stating the typical durations and what they mean in years, months, and signal minutes without turning the conclusion into meaning or exaggeration, and then to ease into a quiet wind-down that maintains the same calm, neutral pace. When the journey to Saturn is measured in human time, the most reliable answer is not a single number, but a bounded range anchored by physics and confirmed by history. A low-energy direct transfer between Earth's orbit and Saturn's orbit, used as a baseline, yields a travel time of roughly 6 years to reach Saturn's distance. This baseline follows from orbital period relationships and from the geometry of a transfer ellipse whose farthest point meets Saturn's orbit. Real missions that follow fuel-efficient logic and that also satisfy practical constraints often arrive on a similar timescale. Cassini, which uses gravity, assists to enable Saturn orbit insertion with manageable launch energy, and arrival conditions takes close to 7 years from launch to orbit insertion. This places the journey in a human calendar as a multi-year project that can be planned and operated within a career, with the spacecraft enduring long cruise conditions before arrival. Faster journeys are also real. The Voyager missions reach Saturn in roughly 3 to 4 years. These times are achieved with higher energy trajectories suited to flyby encounters and onward travel. The shorter time comes with a higher arrival speed relative to Saturn, which fits a fast pass but is not naturally compatible with orbit insertion without large braking. Pioneer 11 reaches Saturn in a little over 6 years after a Jupiter flyby, illustrating another path in the same multi-year range. Taken together, these examples establish that reaching Saturn with known chemical propulsion and gravity-assist design falls most commonly between about 3 years at the fast end for flybys and about 6 to 7 years for efficient routes and for orbit-capable missions. Variations of months around these values occur because launch dates assist sequences and arrival constraints differ. The core remains stable. Saturn travel is counted in years. Human time is not only the cruise duration, it also includes the daily operational time imposed by the speed of light. When a spacecraft is near Saturn, the one-way light time between Earth and the Saturn system is on the order of a little over 1 hour to roughly 1 hour and 20 minutes or more, depending on whether Earth and Saturn are closer or farther in their orbits. This means every command and every confirmation is delayed, and the round-trip time is multiple hours. The mission is therefore operated through pre-planned sequences and onboard autonomy. The delay is a direct translation of distance into minutes, and is independent of how long the spacecraft takes to get there. Even if a faster trajectory shortens the cruise from 6 years to 4, the signal delay near Saturn remains defined by orbital geometry and does not drop below the hour scale. In that sense, Saturn remains remote in operational time even when it is reached as quickly as possible within current mission design. Human time also includes the practical rhythm inside the years. A Saturn mission's cruise is divided into departure, early cruise, mid-cruise, and approach, with the longest span in the middle. In mid-cruise, the spacecraft is mostly coasting under the Sun's gravity, with periodic health checkouts and navigation updates. The mission team measures time in months and years using planned sequences and review cycles. The approach phase in the final months becomes more intensive with increased tracking, trajectory refinement, and rehearsals for arrival operations. Arrival itself is brief compared with the years of travel minutes, or tens of minutes for a major burn hours to days for a close encounter window. Yet arrival is not a sudden surprise. It is a date written into calendars years earlier and then approached through steady correction. This structure is part of what it means to measure the journey in human time. The years are not an empty stretch. They are a planned arc with milestones. The trade-offs that shape this arc can be stated plainly. If fuel efficiency and manageable arrival speed are prioritized, a route similar to a Hohmann transfer or a gravity assist sequence yields a travel time near 6 to 7 years. If shorter time is prioritized and the mission accepts a flyby, a higher energy trajectory can reduce the time to around 3 to 4 years. Pushing below that range would require much higher departure energy, which would reduce payload mass and increase arrival speed, creating difficulty for orbit insertion and increasing exposure to high-speed dust impacts. These constraints explain why Saturn travel does not compress easily into months with known propulsion. At the other end, making the journey much longer is possible by using slower routes that reduce delta V, but longer time increases risk of hardware aging and increases operational cost. Practical missions therefore concentrate in the several-year range that balances energy and endurance. Saturn's motion adds another layer to the meaning of time. Launch windows exist because Earth and Saturn must have the correct phase relationship for the chosen trajectory. These windows recur on the order of a year, but they can be narrowed by other constraints and by gravity assist requirements. Arrival timing is also precise because Saturn does not wait. It moves along its orbit and its moons and rings present changing geometry. A spacecraft must arrive at the correct place and time to perform planned operations. This makes timing a resource. The journey is not only a distance to be covered, but a schedule to be met. In human time, this means the mission is not simply a long drive. It is a planned meeting with a moving world. When the question is framed as how long it would take to reach Saturn, measured in human time, the answer therefore becomes two parallel clocks. One clock counts years of travel, most commonly a few years for fast flybys, and around 6 to 7 years for efficient and orbit-capable missions. The other clock counts the hours of communication delay once the spacecraft is there, typically more than an hour one way. Together they describe what Saturn means in time units that humans already use. Saturn is far enough that reaching it is a multi-year act, and far enough that even after arrival connection remains slow. Within those limits, the journey is still measurable and workable. It is built from the solar system's stable gravitational rules, from a fixed scale set by the astronomical unit, and from trajectory designs that trade energy and time in predictable ways. It is planned in calendars, executed in sequences, and verified through radio signals that carry information across more than an hour of space. These are the measured facts of Saturn travel in human time years, for motion hours for communication, and a moving geometry that turns distance into a schedule.